Look around you at the world in all its vibrant, buzzing complexity. The trees, the birds, the very screen you're looking at, and you yourself, all of it is built from the intricate language of organic molecules. These are the fundamental compounds, rich with carbon, that form the backbone of every living thing. But this fact leads us to one of the most profound and humbling questions humanity has ever asked. Where did they come from? In the beginning, our universe was a searing, empty expanse of hydrogen and helium, a cosmic canvas utterly barren of the chemistry required for life. So how, from that sterile void, did the very first seeds of biology emerge? This isn't just a scientific puzzle. It's a quest to understand our own deepest origins, a story written in the ancient chemistry of the cosmos that long predates the first cell, the first planet, even the first star. We are about to embark on a journey to the very frontier of knowledge, to explore 30 of the most compelling and mind-bending theories for the universe's first organic molecules. Picture the early Earth, a molten world constantly bombarded from space, its young oceans simmering under a toxic sky. Could this chaotic environment have been a crucible, a cosmic kitchen where the basic ingredients of life were cooked up from scratch? Or perhaps the recipe was written elsewhere, in the far-flung nurseries of distant nebulae or on the frozen surfaces of asteroids, with these precious molecular building blocks then hitchhiking across the solar system to eventually seed our world. We will venture into ideas that sound like they're lifted from science fiction, from alien delivery systems and interstellar factories to the sheer, creative power of deep-sea vents and violent lightning strikes. This is the incredible, unfinished epic of how inert stardust first began to arrange itself into the architecture of life, a transition so momentous it touches on the very definition of what it means to be alive in a material universe. So join us as we unravel this greatest of mysteries, tracing the faint chemical pathways that lead from the birth of the cosmos all the way to the spark of life itself. Our journey begins not in the distant stars, but right here at home, with a concept that has captivated scientists and storytellers for nearly a century: the primordial soup. Picture the Earth over 4 billion years ago, a starkly alien world still cooling from its violent formation. Its atmosphere is a thick, toxic blend of methane, ammonia, hydrogen, and water vapor, with no free oxygen to breathe. Vast, simmering oceans cover much of the surface, constantly churned by colossal volcanic eruptions and battered by intense ultraviolet radiation from a young, fiercer sun. It was within this chaotic, hostile environment that two visionary scientists, Alexander Oparin in the 1920s and J.B.S. Haldane independently a few years later, proposed a brilliantly simple idea. They suggested that this entire planet was, in effect, one gigantic chemical laboratory. The early oceans were not just bodies of water, they were a rich, inorganic broth. And the energy sources that racked the young world, the crackle of lightning in the dense skies, the intense heat from volcanic flows, the relentless barrage of UV light, were not agents of destruction but of creation. This constant energy input, they argued, could have provided the spark needed to break and reform the simple chemical bonds in the atmosphere and oceans, gradually shuffling the basic atoms into more complex carbon-based organic molecules. These newly formed compounds would then rain down or wash into the oceans, slowly concentrating over millennia into a nutrient-rich soup. In this vast, warm, dilute broth, the building blocks of life, amino acids, the precursors to proteins and nucleobases, the letters of the genetic code, could have accumulated, setting the stage for even more complex chemistry. For decades, this remained a compelling but unproven thought experiment. Then, in 1953, a young graduate student named Stanley Miller, working under his advisor Harold Urey, decided to test this hypothesis in what would become one of the most famous experiments in all of science. They built an elegantly simple apparatus to mimic the conditions of the early Earth. One flask contained water representing the ancient ocean, which was heated to produce vapor. This vapor was mixed with the gases Oparin and Haldane had proposed: methane, ammonia, and hydrogen in a larger glass chamber representing the atmosphere. Inside this chamber, electrodes created a continuous spark, simulating the lightning that would have been commonplace. The system then included a cooling condenser so that any compounds formed would dissolve in the water and be collected in a trap, just as they might have accumulated in the primordial seas. After letting the experiment run for just 1 week, Miller and Urey analyzed the contents of their miniature ocean. The results were astonishing. The once clear water had turned a murky, reddish-brown, and chemical analysis confirmed it was teeming with organic compounds. Most significantly, they found several amino acids, the fundamental building blocks of proteins, which are essential for life as we know it. This was a monumental breakthrough. For the first time, someone had demonstrated that the basic ingredients for life could arise from simple, non-living chemicals under conditions that plausibly existed on the early Earth. The Miller-Urey experiment instantly became the cornerstone of origin of life research, transforming the primordial soup from a philosophical idea into a tangible, testable scientific framework. It provided a powerful, elegant narrative for how life's journey could have started, not with a miraculous event, but through the relentless, everyday workings of chemistry and physics on a planetary scale. Yet for all its elegance, the primordial soup theory soon began to face its own set of challenges. Scientists realized that the early Earth's atmosphere might not have been as rich in methane and ammonia as Miller and Urey had assumed, potentially making their celebrated experiment less representative of actual conditions. Furthermore, that simmering global ocean was a vast, dilute, and unprotected place. The very UV radiation that provided energy could also just as easily break apart delicate organic molecules, and the emerging building blocks of life were vulnerable, at constant risk of being destroyed almost as quickly as they formed. This puzzle led researchers to search for another kind of cradle, one that was not open and exposed but sheltered and powerful. Their search took them to one of the most extreme and alien environments on our own planet, the crushing, lightless depths of the ocean floor and the spectacular, mineral-rich geysers known as deep-sea hydrothermal vents. Imagine a landscape utterly devoid of sunlight where the pressure is enough to crush a submarine, and the water is just a few degrees above freezing. Then, from cracks in the ocean crust, superheated water, reaching temperatures of over 700 degrees Fahrenheit, blasts forth into the icy darkness. This is not ordinary water, it's a chemical cocktail having been forced down through fissures in the seafloor, heated by the Earth's molten mantle, and becoming saturated with dissolved minerals and gases like hydrogen sulfide, methane, and iron sucked from the surrounding rock. As this incredibly hot, mineral-laden fluid meets the frigid seawater, it precipitates out tiny particles of metal sulfides, creating vast, towering chimney structures that can grow dozens of feet tall. These are the famous black smokers, constantly billowing what looks like dark smoke, which is actually this cloud of mineral particles. There are also white smokers, typically cooler and releasing lighter-colored compounds like barium and silicon. For decades after their discovery, these vents were seen as mere geological curiosities. But then came an even more stunning revelation. These desolate, seemingly inhospitable places were teeming with life. Entire ecosystems, independent of the sun's energy, thrived in the vent's vicinity. Giant tube worms, bizarre clams, and unique shrimp species clustered in the thousands, all sustained not by photosynthesis but by chemosynthesis. Specialized bacteria living inside the worms or free in the water use the hydrogen sulfide spewing from the vent as their energy source, much like plants use sunlight to convert carbon dioxide and water into organic matter. This discovery was a paradigm shift. It proved that life could not only survive but flourish in total darkness, powered solely by chemical energy and the planet's own internal heat. This immediately raised a thrilling possibility. If complex ecosystems could exist here today, could these very same environments have been the birthplace of life's first molecules? The theory posits that hydrothermal vents provide almost everything the primordial soup was missing. First, they offer immense and constant energy. The steep temperature gradient between the scorching vent fluid and the cold ocean creates a natural, sustained flow of energy, a kind of continuous engine. Second, the porous, rocky structure of the vent chimneys themselves acts as a fantastic natural laboratory. Think of them not just as rocks, but as intricate, microscopic honeycombs filled with tiny pores and channels. These confined spaces could have served to concentrate simple precursor molecules, bringing them into close contact and facilitating the chemical reactions needed to build more complex organic chains. The mineral surfaces, rich in iron and sulfur, could have acted as catalysts, lowering the energy required for these reactions to occur, essentially shepherding atoms into the configurations of life. Crucially, these vents are also protected. A mile or more beneath the ocean surface, the nascent building blocks of life would have been completely shielded from the destructive ultraviolet radiation and the violent asteroid impacts that ravaged the surface of the early Earth. The vent environment provides a remarkable combination of raw power and safe harborage. It's a theory that elegantly bridges geology and biology, suggesting that the same planetary processes that built the continents and ocean floors may have also forged, in their deepest, darkest crucibles, the very first ingredients from which all life would eventually arise. But what if we've been looking for the answer in the wrong place entirely? What if the true cradle of life wasn't the deep ocean or a primordial pond, but the vast, cold expanse of space itself? This leads us to our third theory, a concept that stretches the very boundaries of our imagination, Panspermia. The core idea is as simple as it is profound. Perhaps the most fundamental organic molecules, the raw ingredients for life, did not originate on Earth at all. Instead, they were crafted in the frozen laboratories of the cosmos and delivered to our planet pre-made, a celestial gift that kick-started the entire process. Think of our solar system over 4 billion years ago, during a period scientists call the Late Heavy Bombardment. This was a time of incredible violence when countless asteroids and comets screamed through the inner solar system, relentlessly pummeling the young planets. From our perspective, this sounds like an apocalypse, a period of sheer destruction. But from the perspective of Panspermia, this wasn't a catastrophe, it was a delivery service. These cosmic projectiles weren't just barren rocks and balls of ice. We now know, through decades of studying meteorites and cometary dust, that they are treasure troves of complex chemistry. Take, for instance, the Murchison meteorite, a carbon-rich chondrite that fell in Australia in 1969. When scientists analyzed its contents, they found it was studded with a stunning array of organic material, including over 90 different amino acids, some of which are the very same ones used by life on Earth. It also contained nucleobases, the key components of DNA and RNA, and even complex sugars. This wasn't an isolated case. Similar compounds have been found in other meteorites, and observations from powerful telescopes have detected the spectral signatures of complex organic molecules, things like alcohols and even rudimentary sugars, within the swirling gases of giant interstellar clouds and in the glowing comas of comets millions of miles away. So the building blocks of life are not unique to our world. They are a common, almost ubiquitous feature of our galaxy. The theory then asks a logical question. If these molecular seeds are everywhere, and if the early Earth was being constantly seeded by material from space, then the starting point for life's chemistry may have been an import, not a local product. This doesn't necessarily mean that fully formed microbes were riding on asteroids. That's a more specific idea called lithopanspermia. but rather that the foundational toolkit, the amino acids and nucleobases, arrived ready-made. This elegantly solves one of the biggest puzzles for Earth-based origin theories: the scarcity of certain key elements or the instability of forming molecules in a dilute ocean. Instead of having to build every single block from scratch in a challenging environment, the early Earth could have received a constant, rain-down infusion of pre-formed complex organics, significantly enriching the primordial soup and giving it a massive head start. It's a compelling shift in perspective, suggesting that our biological heritage might be interstellar, connecting the chemistry of life on our planet directly to the ancient processes that govern the birth of stars and planetary systems across the cosmos. Yet another possibility takes us to an even more fundamental and widespread cosmic environment: the vast, cold, and seemingly empty interstellar clouds that drift between the stars. For a long time, these nebulous regions were thought to be simple and barren, but we now know they are incredible chemical factories, orchestrating complex reactions on a truly grand scale. The stars of this process are not what you might expect. They are tiny, almost unimaginably small particles known as cosmic dust grains. These are not like the dust you find on a shelf. They are microscopic motes smaller than a wavelength of light, often made of silicates or carbon, forged in the atmospheres of dying stars and then spewed out across the galaxy. Within the frigid, diffuse interior of a molecular cloud, where temperatures can plunge to just 10 degrees above absolute zero, these specks become the stage for a remarkable kind of chemistry. In the near-perfect vacuum of space, the normal rules of chemical reactions where molecules bump into each other in a gas are incredibly slow and inefficient. There's simply not enough density or energy for atoms to frequently collide and stick together. This is where the dust grains provide an essential service. They act as a solid substrate, a microscopic meeting place. Individual atoms and simple molecules like hydrogen, carbon monoxide, and oxygen, drifting through the cloud, eventually bump into a grain and adhere to its icy surface, held by weak forces in a thin, frozen mantle. Stuck in this frozen matrix, these reactants are no longer drifting apart. They are brought into close, intimate proximity, but there's still a problem. At these ultra-low temperatures, the atoms lack the thermal energy to overcome the energy barrier required to form new chemical bonds. They're frozen in place. This is where quantum mechanics performs its magic. A bizarre quantum effect known as tunneling allows these particles to cheat. Even without the classical energy to roll over a hill, a hydrogen atom, for instance, has a certain probability of just seeming to disappear from one side of a tiny energy barrier and instantly reappear on the other. It's as if it dug a tunnel straight through the obstacle. This tunneling effect allows atoms to shuffle around on the grain's surface and meet reaction partners even in the deep cold, enabling chemical unions that would otherwise be impossible. Meanwhile, these clouds are not completely inert. They are constantly bathed in a faint drizzle of high-energy radiation from distant stellar explosions and active galactic nuclei, cosmic rays. When one of these high-energy particles slams into a dust grain, it can deposit a tremendous amount of localized energy, shaking up the icy mantle and kicking off a frenzy of new reactions. It can break apart molecules, creating highly reactive fragments, or provide just the jolt needed for two adjacent atoms to finally link up. Over millions of years, this slow, patient process, sticking, tunneling, and occasional cosmic ray bombardment, builds molecules of surprising complexity. One of the most significant families of compounds thought to form this way are polycyclic aromatic hydrocarbons, or PAH. These are flat, sturdy molecules made of interlocking rings of carbon and hydrogen, essentially microscopic fragments of graphite. We see their unmistakable infrared signatures everywhere in space, in planetary nebulae, in the spiral arms of other galaxies, and even in the meteorites that land on Earth. They are among the most abundant complex organic molecules in the universe. The significance of this is staggering. It means that the very precursors to soot, the same basic structural units found in charcoal and graphite, are being manufactured in colossal quantities in the dark clouds between the stars. These robust carbon rings are thought to be fundamental stepping stones. They could act as platforms for the formation of even more elaborate molecules, perhaps by acquiring side chains of other atoms or serving as anchors for the assembly of the first sugars and nucleobases. So, while the deep sea vents provide a compelling planetary crucible, cosmic dust grain chemistry suggests that the initial steps toward life's molecular complexity began long before our planet even existed, in the silent, frozen depths of interstellar space, on the surfaces of specks of dust so small that trillions of them could fit on the head of a pin. But as we move from the vastness of interstellar space back to our own planet, we encounter a theory that offers a radically different kind of crucible, one that is neither in the deep ocean nor the open atmosphere, but along the dynamic shoreline of the ancient world. This is the radioactive beach hypothesis, a concept that finds power not in the heat of the Earth or the fury of a storm, but in the quiet, relentless decay of unstable atoms. Picture the coastlines of the primordial Earth. These were not the serene, sandy beaches of a modern tropical paradise. They were dramatic, mineral-rich interfaces where the churning, organic-laden waters of the primordial soup met the raw, newly formed continents. And crucially, washing down from the eroding rocks of the interior were dense, heavy minerals, including significant concentrations of radioactive elements like uranium and thorium. Over time, the same wave action that sought sand today would have concentrated these heavy minerals into dense, dark deposits, creating what are essentially natural nuclear reactors spread out along the ancient shores. Now, radioactivity is often framed solely as a destructive force, and it certainly can be. But within the context of the origin of life, it presents a unique and fascinating possibility. The decay of uranium-238 and thorium-232 is a slow, steady process that unfolds over billions of years, releasing a constant, low-level stream of energy in the form of alpha, beta, and gamma radiation. Unlike a lightning strike, which is a single, violent burst, or the intense heat of a hydrothermal vent, which can be chaotic, radioactive decay provides a remarkably stable and sustained energy gradient. It's a persistent, humming power source that never turns off. So, how could this radiation have helped build life's molecules? The key challenge in moving from a primordial soup to a living cell is a process called polymerization. It's one thing to have a collection of individual amino acids or nucleotides, the building blocks floating around in a dilute solution. It's an entirely different problem to get them to link together into long, complex chains like proteins and RNA. Linking these molecules requires energy and a mechanism to remove water molecules, and in a vast ocean, the building blocks are often just too spread out to efficiently meet and react. This is where the radioactive beach offers a compelling solution. First, the shoreline itself acts as a natural concentrator. Waves and tidal action would continually wash the organic, rich seawater over these dense mineral sands, allowing the simple organic molecules to absorb onto the intricate surfaces of the sand grains, bringing them into much closer proximity than they would ever achieve floating freely in the open ocean. Then the radiation takes over. As the radioactive atoms in the sand decay, they emit high-energy particles. When these particles tear through the surrounding water and the concentrated organic scum, they don't just cause destruction, they create a frenzy of what chemists call radicals. A radical is a molecule that has lost an electron, making it highly reactive and desperate to form a new bond to regain stability. This sudden population of radicals buzzing amidst the concentrated building blocks could have provided the necessary activation energy to drive dehydration reactions, forcing the amino acids or nucleotides to link up, releasing water and forming the first primitive polymer chains. Imagine it as a microscopic construction zone where the radioactive sand provides both the workbench that holds the pieces together and the tiny hammers the radiation that fuses them into something larger and more complex. Furthermore, the land-water interface of a beach is a zone of constant wet-dry cycles. As tides recede or puddles evaporate under the sun, the concentrated organic films would go through repeated periods of drying and rehydration. These cycles are known to greatly accelerate polymerization, helping to form more stable and longer chains. So, this theory elegantly combines multiple favorable factors: a natural mechanism for concentrating both the fuel, the radioactive minerals and the feedstock, the simple organics, a sustained, localized energy source, and a physical environment that promotes the necessary chemical reactions. It suggests that the gentle, relentless power of atomic decay, harnessed along the margins of the first continents, could have been the quiet, patient engine that assembled the first sophisticated molecules of life. However, if we shift our perspective from the quiet, patient decay on a beach to the most violent events in our planet's history, we find another compelling possibility. This theory suggests that the very same apocalyptic impacts that once threatened to sterilize the young Earth may have also been powerful, if brutal, architects of life's essential chemistry. We are talking about impact shock synthesis. Cast your mind back to the late heavy bombardment, a period we touched on earlier, but now consider it not as a delivery service for pre-made organics, but as a planet-wide high-energy chemistry set. The Earth's surface was a shooting gallery with asteroids and comets, some dozens of miles across, screaming into the atmosphere at tens of thousands of miles per hour. The kinetic energy of such an object is almost incomprehensible. Upon impact, it is instantaneously converted into a cataclysmic release of heat and pressure. The ground at the point of impact doesn't just melt, it vaporizes, creating a fireball hotter than the surface of the sun. A colossal shockwave ripples outwards, compressing the atmosphere and the crust to pressures millions of times greater than what we experience at sea level. For decades, the scientific narrative focused almost exclusively on the destructive power of these events: the global wildfires, the boiling of oceans, the potential to wipe out any incipient life. But a more nuanced picture has emerged, one that asks a critical question. Could this immense, transient burst of energy have also been a powerful forge for creating new molecules? The key lies in the chemistry of the atmosphere itself. Scientists have run sophisticated computer models and even recreated these extreme conditions in the lab using high-powered shock tubes and laser-driven experiments. They simulate the intense shockwave of an impact passing through a mixture of gases thought to be present on the early Earth, things like carbon dioxide, nitrogen, water vapor, and perhaps some methane. What they've found is remarkable. The sudden, astronomical spike in temperature and pressure doesn't just tear molecules apart. It creates a frantic, chaotic environment where atoms are smashed together with such force that they form entirely new and unexpected bonds. The simple atmospheric gases are essentially shocked into reactivity, recombining into a rich suite of organic compounds. These experiments have successfully produced a whole catalog of life's building blocks, including amino acids, the components of lipids for cell membranes, and even the nucleobases that make up genetic code. It's a paradoxical form of creation through utter devastation. The impact itself is a brief, local apocalypse, but the chemical products of that event, the newly forged organic molecules, could then be spread across the globe by the very same impact plumes that eject material high into the atmosphere, eventually raining down to enrich the planetary soup. This theory provides a fascinating counterpoint to the more gentle, sustained environments like beaches or hydrothermal vents. It suggests that the path to life's complexity wasn't necessarily a slow, steady simmer, but could have been punctuated by violent, planet-altering shocks that periodically injected the environment with fresh, concentrated batches of organic material. The destructive force of an asteroid impact and the creative spark of prebiotic chemistry become two sides of the same cosmic coin. revealing a universe where even its most chaotic and violent phenomena can contribute to the profound and delicate process of building life from non-life. Now, let's turn our attention from the cosmic and geological stages where these molecular building blocks might have formed and focus on the actors themselves. We've been talking about amino acids and nucleobases as if they're the stars of the show, but for life to truly begin, something truly extraordinary had to happen. These building blocks needed to assemble into a molecule that could do two things at once. It had to carry information, a set of instructions, and it had to perform work to execute those instructions. In all modern life, these two jobs are handled by a famous division of labor. DNA is the magnificent library, the stable, long-term repository of genetic information. But DNA is inert. It can't catalyze reactions or build structures. That work is done by proteins, the versatile machines that perform virtually every function in a cell, from digesting food to contracting muscles. But this presents a classic chicken and egg paradox. DNA holds the instructions to make proteins, but proteins are needed to replicate and read DNA. So which came first? How could this interdependent system possibly have bootstrapped itself into existence? The answer to this riddle may lie in a remarkable molecule that acts as a bridge between the two, a jack of all trades that points to a much simpler, more primordial beginning. This is the revolutionary theory known as the RNA world. The central, breathtaking idea is that the first self-replicating system, the very first spark of what we would call life, was based not on DNA but on RNA or ribonucleic acid. Today, RNA is often seen as DNA's less famous cousin, a mere messenger that carries instructions from the DNA library to the protein-building factories. But RNA is far more capable than we once believed. In the early 1980s, the groundbreaking discovery of ribozymes revealed that RNA is not just a passive carrier of information, it can also act as an enzyme. Certain structured RNA molecules can catalyze specific chemical reactions, including the critical task of cutting and joining pieces of RNA itself. This was a monumental revelation. It meant that a single type of molecule, RNA, could potentially perform both of the essential functions of life. It could store genetic information in its sequence of nucleotides, just like DNA, and it could function as a catalyst to speed up and direct chemical reactions, just like a protein. Suddenly, the chicken and egg problem vanished. You no longer needed two separate, interdependent systems to get started. A population of RNA molecules could, in theory, be both the blueprint and the builder. Imagine a single, rare RNA molecule in the primordial soup that, by chance, had a sequence that allowed it to act as a primitive catalyst, a ribozyme that could help link together nucleotides. If this ribozyme could, even clumsily, assist in the assembly of a copy of itself, then you have the beginnings of self-replication. It wouldn't be efficient or pretty at first, but it would be a start. Those molecules that were better at replicating would become more numerous, initiating a rudimentary form of natural selection at the molecular level. The RNA world doesn't claim that the first ribozyme was a sophisticated machine. It might have been a tiny fragment, just a few dozen nucleotides long, capable of performing one simple, sloppy reaction that slightly increased the odds of making a copy. But that's all it would take to cross a critical threshold from chemistry to biology. Of course, this theory immediately raises its own profound question. Where did the RNA molecules themselves come from? How did their specific building blocks, the nucleotides, form without biology to assemble them? A nucleotide is a more complex structure than an amino acid. It has three distinct parts: a sugar ring called ribose, a phosphate group, and one of several nitrogenous nucleobases. Getting these three components to form and then link up correctly in a prebiotic environment is a significant challenge, often called the nucleotide problem. Researchers have been creatively tackling this from multiple angles. One promising line of investigation suggests that the sugar ribose and the nucleobases might not have formed independently and then somehow found each other in a vast ocean. Instead, they could have been synthesized from common precursor molecules on the same mineral surfaces we discussed earlier. For instance, experiments have shown that simple molecules like formaldehyde, which is abundant in space and was likely present on early Earth, can undergo a series of reactions called the Formose reaction to produce a mix of sugars, including ribose. Meanwhile, nucleobases like adenine have been shown to form from hydrogen cyanide, another simple prebiotic compound, under the right conditions. The real trick is getting the sugar, base, and phosphate to all come together. Some laboratory simulations have demonstrated that when these precursor chemicals are exposed to cycles of wetting and drying, or heated in the presence of certain minerals, they can be driven to form the correct linkages, creating the first crude nucleotides. It's a messy process, producing a lot of irrelevant molecules alongside the useful ones, but in a vast, patient planetary experiment lasting millions of years, the improbable becomes inevitable. The RNA world hypothesis provides a powerful and elegant framework that transforms the origin of life from a seemingly magical event into a plausible, stepwise chemical process. It paints a picture of a planet where, after eons of accumulating organic building blocks, the first shimmerings of replication and evolution began not with a cell or a protein or a double helix, but with a single, versatile, self-copying strand of RNA, launching the grand and unbroken chain of life that leads all the way to us. While hydrothermal vents offered a protected crucible deep beneath the waves and radioactive beaches provided a steady, subterranean power source, another immense and inescapable energy stream was constantly bathing the entire planet from above. The young sun, though fainter in total output, was a far more violent and active star, emitting a torrent of high-energy ultraviolet radiation. Unlike today, where our thick ozone layer acts as a planetary sunscreen, the early Earth had no such protection. This relentless UV light was so intense that it would have been lethal to any modern life form, sterilizing the surface and breaking apart fragile organic molecules with ease. But in a fascinating twist of prebiotic chemistry, this same destructive force may have been a master architect, using its power not just to tear down but to build up. The upper atmosphere, a thin veil of simple gases, became a planet-sized photochemical reactor. Imagine molecules of methane, ammonia, water vapor, and carbon dioxide drifting high above the surface, bathed in this constant searing glow. When a photon of UV light carrying a precise packet of energy strikes one of these simple molecules, it doesn't just warm it up, it can break chemical bonds entirely. A methane molecule, for instance, might be shattered into a reactive methyl radical and a hydrogen atom. An ammonia molecule could lose a hydrogen, becoming an amino radical. Suddenly, the calm, stable atmosphere is teeming with these fragmented, highly reactive pieces, each one an atomic shard desperate to form a new bond to regain stability. This is where the magic happens. These radical fragments created by the sun's destructive power don't just vanish. They collide with each other in the dense lower atmosphere, recombining in a near-infinite number of new configurations. It's a chaotic, continuous atomic shuffle driven by solar energy. A methyl radical from methane might link with an amino radical from ammonia, potentially forming methylamine, a simple organic compound. Further reactions, perhaps incorporating a carbon monoxide molecule or a hydroxyl radical from split water vapor, could build these up into even more complex structures like the amino acids glycine or alanine. This isn't just theoretical. The famous Miller-Urey experiment, which used electrical sparks, also produced positive results when researchers substituted the spark discharge with a powerful UV lamp, demonstrating that ultraviolet light alone could indeed drive the synthesis of life's building blocks. The scale of this process would have been global and relentless. these newly formed, more complex organic molecules would have been relatively heavy compared to the atmospheric gases. They would have slowly drifted down through the skies, condensing onto dust particles or dissolving into water droplets, eventually raining down into the waiting oceans and lakes below. This provides a compelling solution to the dilution problem that plagues some ocean-based origin theories. Instead of trying to form complex molecules in a vast, dilute sea, the atmosphere acts as a highly efficient, planet-wide concentrator and factory. The reactions happen in a gaseous medium where collisions are frequent, and the finished products are then delivered directly to the surface in a constant, gentle drizzle of organic rain, steadily enriching the primordial soup with a rich inventory of prebiotic compounds. So, while the surface environment below may have been too hostile for delicate chemistry, the sky itself was alight with creative potential, transforming the very radiation that seemed to forbid life into one of its most prolific and generous builders. While our journey has taken us to the depths of the ocean and the far reaches of space, one of the most compelling stages for life's origin might be found in the most humble of earthly materials, mud. This is the theory of clay mineral catalysis, and it proposes that the very ground beneath our feet, or more specifically, the intricate microscopic world of certain clays, could have been the nursery where inanimate chemistry first crossed the threshold toward biology. The central challenge for any origin of life scenario is moving from a chaotic mixture of simple organic building blocks to the highly ordered, long-chain polymers essential for life. How do you get individual amino acids to reliably link up into proteins, or single nucleotides to assemble into the long strands of RNA, especially in a watery environment where the reaction to form these chains actually releases a water molecule? In the vast, dilute primordial soup, this process, known as polymerization, is incredibly inefficient. It's like trying to build a skyscraper in the middle of the ocean, with the waves constantly threatening to wash your bricks away before you can cement them together. This is where certain clay minerals like montmorillonite enter the picture not as passive dirt but as dynamic, active participants. These clays form in the weathering of volcanic rocks and are incredibly common. Their secret power lies in their intricate layered crystalline structure. Imagine a microscopic deck of cards where each card is a sheet of aluminosilicate, just a few atoms thick. These sheets carry a slight negative electrical charge, but the real magic happens in the gaps between them, called the interlayer spaces. These spaces are filled with positively charged ions like sodium or calcium, which act as bridges and, crucially, with water molecules. This creates a unique environment, a protected, highly structured, and charged nanoscale landscape. For the simple organic molecules floating in the early seas, these clay particles would have acted like powerful molecular magnets. The charged surfaces attract and absorb the organic monomers, pulling them out of the dilute solution and concentrating them along the clay's surface and within its interlayer galleries. This close confinement is a game changer. Instead of floating meters apart, the building blocks are now lined up side by side, dramatically increasing their chances of interacting and reacting with each other. But the clay does more than just gather the ingredients. It also provides the instructions and the tools. The repeating, ordered pattern of atoms on the clay's surface can act as a template, guiding the way the organic molecules align. Some researchers suggest that the specific spacing and charge distribution on a clay surface could have helped nucleotides line up in a particular order, effectively acting as a primitive, non-biological form of information storage, a rough draft for what would later become the genetic code. Even more impressively, the clay's surface isn't just a passive stage, it can be a catalyst. The charged sites on the clay can help polarize the molecules stuck to it, making them more reactive. They can also help facilitate the key chemical step of dehydration, effectively pulling water molecules away from the reacting monomers and making it much easier for them to link together into a polymer chain. Laboratory experiments have stunningly confirmed this catalytic power. When a solution of activated nucleotides, the building blocks of RNA, is poured over a bed of montmorillonite clay, the clay doesn't just passively sit there. It actively promotes the formation of RNA chains over 10 units long, and in some cases even up to 50 units, simply through the process of drying and rewetting. This is a monumental result. It demonstrates that a common, inorganic mineral can perform one of the most critical steps in the origin of life, creating long, information-capable molecules from a random soup of parts without any biological help. Yet the role of clays might extend even further into the realm of creating the very first boundaries of life. As these newly formed organic polymers accumulated on the clay surfaces, they could have interacted with other molecules like fatty acids, which are the precursors to cell membrane. Fascinatingly, experiments have shown that when lipids are present, they can spontaneously form tiny, cell-like vesicles around clay particles that have RNA molecules stuck to them. Picture this: a speck of clay coated in a newly synthesized strand of primitive RNA becomes encased in a protective bubble of fatty molecules. This isn't a living cell, but it's a breathtakingly profound protocell, a compartment that separates a tiny, organized internal environment from the chaotic outside world. The clay, in this scenario, is not just a catalyst and a template. It becomes the very heart and scaffold around which the first semblance of a cellular structure can assemble. This theory offers a beautifully simple and elegant narrative. It suggests that the transition from chemistry to biology did not require a miraculous event in some exotic, hard-to-find location. Instead, it could have begun in the most ordinary of places, in the mudflats at the edges of hot springs, or in the sediments of ancient rivers and lakes, where common clay minerals provided the order, the energy, and the architectural guidance to shepherd random molecules toward the breathtaking complexity of life. But this journey through the chemical possibilities of our young world now takes us back to the seafloor, to a distinct and, in many ways, even more promising type of hydrothermal system. While the towering black smokers with their billowing, superheated, metal-rich plumes capture the imagination, another kind of vent exists, one that is quieter, more diffuse, and potentially far more significant for the origin of life. These are alkaline hydrothermal vents, and their unique chemistry arises from a profound geological process known as serpentinization. The drama begins not with a violent volcanic eruption, but with a slow, persistent chemical reaction deep within the Earth's oceanic crust. Imagine seawater, cold and rich in dissolved carbon dioxide, seeping down through vast networks of cracks and fissures in the seafloor. It continues its descent until it reaches a layer of rock known as peridotite. This isn't just any rock, it's ultramafic rock, a relic of the Earth's mantle that has been thrust upward, composed primarily of minerals like olivine and pyroxene, which are rich in iron and magnesium. When this mineral-rich water comes into contact with the peridotite, something remarkable happens. The water itself is not just a passive spectator, it becomes a reactant. In a process that is exothermic, meaning it releases a tremendous amount of heat, the water molecules are chemically incorporated into the crystal structure of the rock's minerals, transforming them into a new, greenish, serpentine-like mineral family, hence the name serpentinization. This metamorphic reaction is a chemical powerhouse with two critical byproducts. First, it releases vast quantities of hydrogen gas. The iron in the olivine, which is in a ferrous state, reacts with the water, oxidizing to a ferric state and, in the process, stripping oxygen from the water molecules and liberating hydrogen. Second, it makes the surrounding fluid highly alkaline with a pH that can soar to levels as high as 9, 10, or even 11. This is as basic as household bleach. So, we have a system that is continuously producing two things life craves: a potent, accessible fuel in the form of hydrogen gas and a steep chemical gradient. This hydrogen-rich, highly alkaline fluid doesn't stay trapped underground. It percolates back upwards, seeking a path to the ocean above. when it finally vents into the cold, acidic, and carbon dioxide-rich seawater, which has a pH of around 5 or 6, it creates an interface of immense chemical potential. This isn't just a mixing of hot and cold, it's a collision between two profoundly different chemical worlds, and at this boundary, within the porous, rocky structures that form as the warm fluid precipitates minerals, something incredible can occur. The hydrogen gas rising from below is a powerful reducing agent eager to donate electrons. The carbon dioxide dissolved in the ocean water is an oxidizing agent ready to accept them. This natural redox imbalance is a form of stored energy, a chemical battery waiting to be tapped. Laboratory experiments and sophisticated models have shown that in the presence of certain mineral catalysts, like the iron-sulfur clusters found in the vent rocks, this disequilibrium can drive what is known as the reverse Krebs cycle or acidogenesis. This is a suite of reactions where hydrogen reduces carbon dioxide, step by step, to build up more complex organic molecules, starting with formate and acetate and potentially leading to the pyruvate and other central metabolites that sit at the heart of all modern biochemistry. It's a way of fixing carbon and building life's molecular scaffolding directly from the most basic planetary ingredients. But the parallels to life run even deeper into the very way cells power themselves. All living cells maintain a slight electrical imbalance across their membranes, a difference in the concentration of protons, which are hydrogen ions. This proton gradient acts like a miniature battery, and the flow of protons back across the membrane through special proteins is what drives the production of ATP, the universal energy currency of the cell. For decades, how such a sophisticated system could have evolved was a major mystery. Astonishingly, alkaline hydrothermal vents provide a ready-made, non-biological blueprint. The vent structures themselves are not solid walls. They are often a porous, labyrinthine matrix of microscopic compartments and channels with walls that are semi-permeable. The fluid inside these pores is the alkaline, hydrogen-rich product of serpentinization. The ocean outside is acidic. This creates a natural proton gradient across the inorganic mineral walls of the vent, a sustained pH difference that is chemically identical in principle to the one that powers every living cell. The natural flow of protons from the acidic ocean into the alkaline microcavities represents a continuous prebiotic form of energy, a geochemical engine that could have been harnessed by the first primitive metabolic systems. These porous rocky mounds, therefore, are not just chemical reactors. They are, in effect, the world's first and most fundamental batteries, offering not only the building blocks of life, but also the very energy dynamic required to assemble them into something more complex. They present a holistic and deeply compelling scenario where geology, chemistry, and the foundational principles of biology converge in a single, remarkable environment. As we've seen, the dark molecular clouds between stars are far from empty. They are dynamic chemical arenas where tiny dust grains provide a stage for complex reactions. But there's another layer to this cosmic chemistry, one that transforms these microscopic specks into miniature cryogenic laboratories. This is the world of cosmic ice mantles, where the profound cold of space becomes an essential ingredient for building life's precursors. Within these vast, frigid clouds, temperatures hover just a few tens of degrees above absolute zero. At these extremes, gases that would normally remain separate and aloof in the void don't just bump into dust grains and stick. They freeze solid, forming a thin, icy crust coating each grain. Imagine a tiny grain of silicate or carbon, perhaps only 1/1000th of a millimeter across, acting as a seed. Onto its surface, a fragile frost slowly accumulates, not just water ice, but a complex cocktail of molecules that have frozen out of the surrounding gas. This isn't a pure crystalline ice like you'd find in a freezer. It's a mixed amorphous mantle, a chaotic jumble of water, carbon monoxide, carbon dioxide, methane, ammonia, and methanol, all frozen together in a solid matrix. This icy coating is the key. It's a frozen repository of simple molecules trapped in close proximity. In the near-perfect vacuum of a molecular cloud, these ices can persist for millions of years, but they are not dormant. They are constantly being processed by two powerful external forces: the faint but pervasive drizzle of ultraviolet photons from distant stars and the occasional, immensely energetic punch of a cosmic ray. When a UV photon slams into an ice mantle, its energy is absorbed, causing molecular bonds to vibrate, stretch, and ultimately break. A water ice molecule might be shattered into a hydroxyl radical and a hydrogen atom. A molecule of methane could be torn apart into a methyl radical and a hydrogen atom. These newly created fragments, known as radicals, are highly unstable and desperate to form new bonds. Trapped within the rigid, frozen lattice of the ice, they can't simply float away. Instead, they remain caged, vibrating and wiggling, until by chance they encounter another radical or a still intact molecule right next to them. The ultra-cold temperature, which seemed like a barrier to chemistry, now becomes a facilitator. It keeps these reactive fragments locked together long enough for quantum tunneling to occur, allowing them to merge and form entirely new, more complex molecules that would never have formed in a warmer gas. This process is dramatically amplified by cosmic rays. These subatomic particles, traveling at nearly the speed of light, carry enormous energy. When one penetrates a dust grain and its ice mantle, it acts like a microscopic bomb, creating a localized hotspot and a cascade of secondary reactions, breaking countless bonds and creating a frenzy of radicals in its wake. As the ice slowly warms up again, perhaps as the cloud begins to collapse to form a new star, these newly forged complex molecules are released from their icy prison, enriching the surrounding gas cloud. The evidence for this incredible process is not just theoretical. We see it with our telescopes. Astronomers using infrared observatories can detect the specific absorption signatures of these ices in molecular clouds. Even more stunningly, they have identified the spectral fingerprints of more complex organic molecules within these ices, including compounds like formamide, which is a direct precursor to amino acids and nucleobases. Laboratory experiments here on Earth perfectly replicate these conditions. Scientists create ultra-high vacuum chambers, cool surfaces to just a few degrees above absolute zero, and deposit thin layers of mixed ices identical to those in space. They then irradiate these ices with UV lamps or simulate cosmic ray bombardment. Consistently, these experiments show that the clear, simple ices gradually turn a yellowish brown, a color we also observe in space, nicknamed cosmic cyanogen. And when the ice is warmed and analyzed, it is found to contain a rich, tar-like residue teeming with organic compounds. This residue contains amino acids like glycine, the components of sugars, and even the nucleobase adenine. This means that the fundamental letters of our genetic code and the building blocks of our proteins can be, and are being, manufactured in the frozen depths of interstellar space on the surfaces of countless dust grains long before a star and its planets even form. When a new planetary system like our own eventually coalesces from such a cloud, these complex organics are already baked into the recipe. They become part of the comets, asteroids, and planetesimals, ensuring that young worlds like the early Earth are seeded from the very beginning with a rich inventory of life's potential ingredients, a chemical legacy inherited directly from the cold, dark nurseries of the cosmos. Moving from the deep sea vents and the frozen depths of space, our search for life's origins brings us back to the most dramatic and visceral landscapes of the young Earth, its raging, fire-breathing volcanoes. While we've already considered the raw heat and mineral wealth of these geological giants, there's a specific, electrifying phenomenon associated with their fury that offers a uniquely powerful pathway for chemistry. This is the theory of electric discharge within volcanic plumes, a concept that brilliantly merges the energetic principles of the primordial soup with the intense, localized conditions of an erupting volcano. Picture the scene of a massive volcanic eruption on the early planet. It's far more than just lava and ash. It's an atmospheric event of staggering proportions. A colossal plume, thick with incandescent ash particles, superheated water vapor, and a cocktail of gases like carbon dioxide, nitrogen, and sulfur compounds, punches high into the atmosphere. This churning, turbulent cloud is not a calm, steady stream. It's a maelstrom of colliding particles where ash and rock fragments rub against each other at tremendous speeds. Just as rubbing your feet on a carpet builds up a static charge, this violent friction within the plume generates immense electrical potential, creating a natural, continuous electrical generator on a colossal scale. And where you have a massive charge separation, you get lightning. These aren't the familiar bolts from a thundercloud. This is volcanic lightning, a spectacular and terrifying display of raw power flashing within the very heart of the eruption itself. Now, recall the Miller-Urey experiment, where a spark in a flask of simple gases produced amino acids. A volcanic plume presents a natural, planet-wide version of that famous apparatus, but with several dramatic advantages. First, the flask is the plume itself, an enormous turbulent reactor filled with the very gases thought to be present in the early atmosphere. Second, the electrodes are the countless volcanic lightning strikes, each one a concentrated burst of energy capable of breaking and reforging chemical bonds. When a bolt of lightning tears through this dense mixture of gases and ash, the intense heat and shockwave create a temporary, super-energized plasma. Within this microscopic fireball, the stable molecules of carbon dioxide, nitrogen, and water vapor are shattered into their constituent atoms and highly reactive radicals. As this tiny inferno rapidly cools, these fragments furiously recombine. But they don't just reassemble into what they were before. The chaotic energy forces them into new, more complex configurations. A carbon atom from a shattered carbon dioxide molecule might latch onto a nitrogen atom, forming a cyanide radical, a cornerstone prebiotic molecule. That cyanide could then react with other fragments, potentially stepping its way toward amino acids or nucleobases. The diversity of molecules formed could be far greater than in a simple atmosphere, because the plume is not just gas, it's also laden with fine ash particles. These microscopic grains provide vast surface areas, acting as catalysts to shepherd specific reactions and protect the newly formed, delicate organic molecules from being destroyed by the next flash of energy. Furthermore, the plume offers a perfect delivery mechanism. These newly synthesized compounds, clinging to the ash particles or dissolved in condensing water vapor, would be carried high into the sky by the eruptive force. Then, as the plume spreads and cools, they would rain down across the globe, blanketing the land and sea with a fresh infusion of organic material. This theory elegantly addresses a key weakness of the classic primordial soup idea, the problem of dilute concentration. Instead of relying on a slow, planet-wide buildup, each major volcanic eruption could have acted as a localized, hyper-efficient organic factory, producing a concentrated pulse of life's building blocks and distributing them widely. It links the planet's most destructive forces with its most creative chemistry, suggesting that the very fires that shaped the early Earth may have also, through their spectacular electric fury, forged the foundational molecules from which life would eventually arise. Yet as compelling as alkaline vents and volcanic lightning may be, a truly revolutionary idea emerged from the world of patent law and chemistry, one that completely upended the notion of a free-floating primordial soup. This is Gunther Wechtersheuser's iron-sulfur world theory, a hypothesis that proposes life did not begin in the water at all, but on a solid, glittering surface, the brassy, metallic mineral known as pyrite or fool's gold. Wechtersheuser, a man whose background outside conventional academia gave him a uniquely bold perspective, suggested that the very first life-like processes were not floating in a dilute ocean, but were firmly anchored, a kind of two-dimensional life living on a rock. The cornerstone of his theory is a simple but powerful geochemical fact. When pyrite forms, it has a remarkable property. It grows from the reaction between iron sulfide and hydrogen sulfide, a process that actually releases electrons. This means the surface of a growing pyrite crystal develops a strong positive electrical charge. Now, imagine the early Earth's oceans, which we believe were already rich with a variety of simple, negatively charged organic molecules, things like carboxylic acids or phosphate groups. According to basic chemistry, opposites attract. This positively charged pyrite surface would have acted like a powerful molecular magnet, pulling these negatively charged organic compounds out of the water and binding them tightly, concentrating them from a sparse soup into a dense, reactive film directly on the mineral's surface. This simple act of concentration solves a monumental problem. In a vast ocean, getting enough molecules together to react is a slow, chancy affair. On the surface of pyrite, the building blocks of life are suddenly arranged elbow to elbow, dramatically increasing the odds that they will interact and undergo further chemical transformations. But the pyrite does more than just gather the ingredients, it also provides the energy to cook them. The formation of pyrite itself is an exothermic reaction. It gives off heat. Hydrothermal proposed that this continuous, sustained energy release from the growing crystal could have powered the chemical reactions that assembled those simple organics into more complex chains. In his vision, the surface of the pyrite wasn't just a passive stage, it was the engine. This leads to the theory's most profound departure from other ideas, the concept of a surface metabolism. Before the first cell membrane ever formed to create a tiny, enclosed compartment, Hydrothermal argues that the first cycles of life-sustaining chemistry could have begun right there on the flat, two-dimensional landscape of the pyrite crystal. He envisions a cascade of chemical reactions where the products of one reaction become the starting materials for the next, all organized and driven by the energy and catalytic properties of the mineral surface. This nascent metabolic network would be pinned in place, a primitive, non-living chemical system that nonetheless begins to exhibit a key characteristic of life. It draws energy from its environment to create and maintain order. To draw an analogy, think of a modern city. The iron-sulfur world isn't proposing that a fully formed city suddenly appeared. It's suggesting that the first thing to emerge was the foundational grid of streets and power lines, the metabolic pathways. Only later would individual buildings, the protocells, arise within this already functioning infrastructure. The pyrite surface provides that initial grid, a structured environment where energy flows and chemicals are processed in an orderly way. This surface-based beginning also offers an elegant solution to the puzzle of how the first genetic molecules could have been replicated without modern enzymes. On a charged crystalline surface, the components for a primitive RNA-like molecule could line up in a specific order, templated by the mineral's own geometric pattern. The energy from pyrite formation could then help link these components together, and the resulting chain would remain stuck to the surface, ready to act as a template for its own copy. This idea of a two-dimensional world challenges our very conception of life's cradle, moving it from a watery, chaotic soup to the structured, energetic, and solid ground of a mineral that was undoubtedly common on the volatile early Earth. It paints a picture of life's dawn not as a solitary spark in a vast ocean, but as a vibrant chemical film clinging to the surfaces of fool's gold, taking its first metabolic breaths long before it learned to swim. Yet all these terrestrial and interstellar environments share one common challenge: the sheer vastness and dilution of space and time. For chemistry to build something as intricate as a living system, it often requires not just energy and ingredients, but also a way to concentrate and protect those ingredients, allowing reactions to proceed over meaningful timescales. This brings us to a theory that offers a perfect, self-contained solution, the cometary factory model, which envisions these icy wanderers as self-sufficient, mobile chemical laboratories. We often think of comets as simple, dirty snowballs, but modern science reveals them to be among the most chemically complex objects in our solar system. A comet's nucleus is a primordial relic, a frozen archive from the solar system's birth, composed of a heterogeneous mixture of water ice, frozen gases like carbon monoxide and carbon dioxide, and a generous amount of dark, carbon-rich dust and complex organic material. This isn't a homogeneous block of ice, it's more like a porous, fragile amalgamation of ices and rocky dust, often compared to a cosmic dusty ice cube or a loosely packed rubble pile. For most of its long, elliptical orbit, a comet resides in the deep freeze of the outer solar system, where temperatures are only a few dozen degrees above absolute zero. In this state, its chemistry is slow, preserved in a kind of suspended animation, similar to the ices on interstellar dust grains. But the magic begins when its orbit brings it swinging in toward the Sun. As a comet approaches the inner solar system, solar heating begins to vaporize the volatile ices on its surface, creating the magnificent coma, the glowing, gaseous envelope that can be millions of kilometers across, and the iconic tails that stream away from the Sun. This process, known as outgassing, is far more than just a pretty light show. It is the activation of a sophisticated chemical factory. The heat from the Sun doesn't just vaporize the ices, it provides the activation energy to drive reactions that were impossible in the deep cold. The comet's nucleus becomes a dynamic, layered chemical reactor. The surface, exposed to direct sunlight, becomes active and loses material, while just beneath the surface, in a region scientists call the sublimation front, the ice is turning directly into gas. This creates a complex environment where molecules are constantly on the move, percolating through the porous interior, encountering new reaction partners, and being exposed to new energy sources. But solar heating is only one part of the energy equation. Throughout its entire life, even in the cold outer darkness, a comet's nucleus is constantly being irradiated by cosmic rays. These high-energy particles can penetrate deep into the icy body, breaking molecular bonds and creating a population of highly reactive radicals, just as they do in interstellar ice mantles. These radicals remain trapped, frozen in place, waiting. Then, as the comet heats up, this stored chemical energy is released. The radicals gain mobility and begin to combine, initiating a cascade of new reactions that synthesize more complex organic molecules from the simple, frozen precursors. The physical structure of the comet is crucial here. The porous, dust-laden interior provides an immense surface area, a vast, intricate network of tunnels and cavities where molecules can adhere and interact. The dust grains themselves, often rich in metals and minerals, can act as catalysts, lowering the energy required for specific reactions and guiding the chemical pathways toward the formation of biologically relevant compounds. This entire process was spectacularly confirmed by the European Space Agency's Rosetta mission, which spent 2 years orbiting comet 67P Churyumov-Gerasimenko. Rosetta didn't just fly by, it became a constant companion, analyzing the comet's composition as it transformed on its journey around the Sun. The findings were nothing short of revolutionary. The Rosetta spacecraft and its Philae lander detected a stunning variety of organic molecules in the comet's coma and on its surface. They found glycine, the simplest amino acid, alongside its precursor molecules methylamine and ethylamine. They detected phosphorus, a key element for life and a crucial component of the backbone of DNA and RNA. Perhaps most impressively, they found a whole host of other complex organics, including alcohol and carbonyl compounds. This wasn't just a handful of simple ingredients. It was a rich, diverse chemical inventory, demonstrating that comets are indeed active factories, capable of producing a wide spectrum of the molecular building blocks essential for life. The significance of this extends beyond mere detection. The cometary factory model provides a mechanism for creating and delivering these compounds in a protected package. A comet is in effect a natural spaceship with a refrigerated cargo hold. It can synthesize complex molecules in its warm, active phase, and then, as it travels back to the outer solar system, it refreezes, preserving its precious organic cargo for millions of years until its next voyage or a chance encounter with a planet. When a comet or fragments of it collide with a young world like the early Earth, it doesn't just deliver a random assortment of simple chemicals. It delivers a concentrated payload of pre-processed, complex organic material, effectively jump-starting the planet's prebiotic chemistry with a sophisticated molecular toolkit. This model elegantly merges the ideas of cosmic chemistry with planetary seeding, presenting comets not as simple celestial projectiles, but as one of the most prolific and efficient factories for life's ingredients in our entire solar system. Yet another fascinating possibility takes us away from the deep sea and the cold of space to the dynamic, sun-drenched margins of the ancient continents, the tidal flats and evaporating lagoons. Here, a niche but remarkably compelling idea known as the prebiotic pizza hypothesis suggests that the very recipe for life's first molecules might have involved a kind of geological layering, creating a structured environment where chemistry could thrive. Imagine a broad, shallow lagoon on the primordial Earth, repeatedly flooded by tides rich with simple organic compounds washed in from the ocean, and then exposed to the heat and wind as the water recedes. This constant cycling between wet and dry is the first crucial ingredient. When the lagoon is full, it acts as a collecting pool, gathering amino acids, nucleotides, and other building blocks from the surrounding waters. But as the sun beats down and the water slowly evaporates, something transformative happens. The solution becomes more and more concentrated, driving the dissolved organics out of the water and forcing them to deposit onto the solid surfaces beneath. The mud, the sand, and most importantly, the intricate layers of different minerals that form the lagoon bed. This is where the pizza analogy comes to life. Just as a pizza is built with a foundation of dough, then sauce, then cheese and toppings, a prebiotic tidal flat could have developed a stratified structure. The base layer might be a common clay like montmorillonite, which we know is excellent at absorbing and concentrating organic molecules. On top of that, a layer of evaporite minerals like gypsum or halite could form as the water disappears, creating crystalline structures that further trap and organize the chemical ingredients. Another layer might be rich in iron sulfide or other metal oxides that can act as catalysts. With each successive cycle of wetting and drying, new layers of organics and minerals are deposited, creating a dense, multi-layered chemical sandwich. This stratified environment solves several major problems at once. First, the concentration effect is enormous. Instead of molecules being hopelessly diluted in a vast ocean, they are squeezed together in these thin, concentrated films, dramatically increasing their chances of colliding and reacting. Second, the different mineral layers aren't just passive holders. Each one can provide a unique chemical service. One type of clay might be particularly good at aligning nucleotides to encourage them to form chains, while an adjacent metal sulfide layer could provide the catalytic power to actually drive the linking reactions, and a carbonate layer could help maintain a specific pH level that favors certain chemical pathways. The wet-dry cycles themselves are a powerful engine for polymerization, the process of linking small molecules into long chains. Every time the lagoon dries out, the removal of water directly promotes dehydration synthesis, which is the chemical reaction that hooks building blocks together while releasing a water molecule. When the area is flooded again, the new polymers are rehydrated and can interact, perhaps even being released from the mineral surfaces to mix and find new partners before the next drying cycle concentrates them once more. This repetitive process, happening over countless generations, could have steadily built up longer and more complex molecules, from short peptides to primitive strands of RNA, all within the protected, structured, and energy-rich confines of this geological pizza. It's a theory that finds power not in a single dramatic energy source like a lightning bolt or a hydrothermal vent, but in the patient, rhythmic pulsing of the tides and the slow, layered accumulation of ingredients, creating a sophisticated prebiotic kitchen at the quiet boundary between land and sea. Now, let's shift our perspective from the gradual processes of Earth and the quiet chemistry of interstellar space to consider a force of almost unimaginable power and violence, a phenomenon so immense it can outshine entire galaxies in a matter of seconds. This brings us to a theory that is as spectacular as it is speculative: gamma-ray burst synthesis. To understand this idea, you first have to grasp the sheer scale of a gamma-ray burst. These are not merely large explosions, they are the single most energetic events known to occur in the universe since the Big Bang itself. Imagine a star many times more massive than our Sun reaching the end of its life. Instead of a typical supernova, its core collapses directly into a black hole, and from its poles it fires two opposing beams of concentrated energy beams composed of the highest energy form of light, gamma radiation. These jets, moving at almost the speed of light, carry in seconds more energy than our Sun will emit over its entire 10 billion-year lifetime. If one of these beams were to be pointed directly at a planetary system, even from thousands of light years away, the effects would be cataclysmic. For a brief moment, that distant world would be bathed in a flash of radiation so intense it would deliver the equivalent of 1,000 years' worth of solar UV radiation in just a few seconds. For decades, the scientific discussion around such an event striking the early Earth focused almost exclusively on its potential as an agent of mass extinction, a sterilizing flash that could wipe out any incipient life. But a more nuanced and fascinating question has emerged from the ruins. Could such an apocalyptic delivery of energy also have a creative side? The theory of gamma-ray burst synthesis posits that this incredible influx of energy, while devastating on a global scale, might have acted as a planet-wide chemical forge, driving reactions in the upper atmosphere that were simply impossible under any other condition. Here's how it might have worked. The early Earth's atmosphere was a thick blanket of gases like nitrogen, carbon dioxide, water vapor, and methane. When the gamma-ray flash hit, it wouldn't just warm the air, it would rip it apart. The high-energy photons would tear electrons from their atoms, creating a superheated plasma and shattering stable molecules into a chaotic soup of their constituent atoms and highly reactive, charged fragments known as ions. For a short time, the upper atmosphere would become a seething inferno of fundamental particles, but destruction on this scale sets the stage for a unique kind of creation. In the immediate aftermath of the burst, as the atmosphere began to cool and restabilize, this frantic swarm of atomic and ionic fragments would start to recombine. And this is where the theory gets particularly interesting. The sheer density of these reactive pieces, all trying to find new partners at once, could force atoms into chemical marriages that are highly unusual. The normal, gentle pathways to organic molecules involve step-by-step additions, building complexity slowly. A gamma-ray burst, by contrast, provides a single, monumental shock to the entire system, potentially skipping several intermediate steps and jumping directly to complex configurations that are thermodynamically unfavorable under common circumstances. It's the difference between carefully assembling a watch and throwing all its parts into an explosion. Most of the time you get junk, but very, very rarely, the force of the blast might snap a few pieces together in just the right way. In this frantic recombination phase, carbon atoms shattered from methane could link with nitrogen atoms from torn apart nitrogen gas, forming cyanide compounds which are actually crucial prebiotic precursors. Ions and radicals might be driven to form acetylene or other exotic hydrocarbons. Some laboratory experiments that simulate intense radiation environments, though on a much smaller scale, have shown that such conditions can produce a wider variety of complex organic molecules, including some with unusual ring structures that are not commonly seen in other prebiotic simulations. The resulting organic haze, a global smog of newly forged compounds, would then slowly settle out of the sky, raining down onto the surface and oceans below. This wouldn't be a gentle, continuous drizzle like from photochemistry, but a single, massive pulse of organic delivery, a sudden enrichment of the planetary soup with a unique and diverse set of molecular ingredients. Of course, the viability of this theory hinges on a delicate and terrifying balance. The gamma-ray burst must be close enough to deliver a significant energy dose to the atmosphere, but not so close that it vaporizes the oceans and strips the entire atmosphere away. Calculations suggest a Goldilocks zone of maybe 6,000 to 10,000 light-years away. It also must be an incredibly rare event. The odds of a planet being struck by such a beam in the window of time when it is primed for life are vanishingly small. But in a universe with hundreds of billions of galaxies, each with hundreds of billions of stars, the improbable becomes inevitable somewhere. For Earth, it remains a long shot, a cosmic lottery ticket with an almost infinitely small chance of winning. Yet it forces us to consider a truly profound notion, that the very same kind of event that could snuff out life across a planet might also, under the right circumstances, provide the unique chemical spark that helps to ignite it, weaving the most violent explosions in the cosmos directly into the narrative of our own origins. This continuous, planet-wide search for the cradle of life leads us from the ocean abyss back onto the very continents themselves, to the steamy, bubbling landscapes of terrestrial hot springs and sprawling geothermal fields. While we've explored the deep sea vents with their immense pressures and alien ecosystems, these land-based systems offer a distinct and equally compelling set of advantages. Picture a volcanic region on the young Earth, not with cataclysmic eruptions, but with a persistent, gentle heat rising from below. The ground is warm to the touch, and from countless fissures and porous rocks, hot water percolates steadily to the surface, carrying with it a dissolved treasure trove of minerals leached from the bedrock below. These are not fleeting puddles, they are stable, long-term environments that could have persisted for thousands or even millions of years, providing a remarkably consistent and protected stage for chemistry. The magic of these systems lies not just in their heat but in their dynamic flow. Imagine rainwater or water from condensed volcanic steam seeping deep into the ground. As it descends, it's heated by the Earth's internal magma chambers, and because hot water is an excellent solvent, it becomes saturated with a rich mix of elements: silica, sulfur, boron, potassium, and critically, dissolved metals like iron, zinc, and manganese. This mineral-rich cocktail then rises back towards the surface, forced upward by geothermal pressure, moving slowly and continuously through a labyrinth of cracks, pores, and channels in the surrounding rock. This slow, persistent journey through porous rock is where a remarkable process akin to a natural chromatography column takes place. In a laboratory, chromatography is a technique used to separate a mixture by passing it through a medium where different components travel at different speeds. In a geothermal field, the porous volcanic rock acts as that medium, and the continuous flow of hot water is the moving solvent. As this fluid, laden with a messy mixture of simple organic molecules from atmospheric or subterranean sources, percolates upward, something fascinating happens. Not all molecules are created equal. Some have a stronger tendency to stick to the surfaces of the rock grains, while others are more easily carried along by the water. Some are larger and get temporarily trapped in narrower pores, while smaller ones slip through easily. This creates a natural sorting mechanism. Over time and distance, the originally mixed jumble of organics begins to separate out. Specific types of molecules, based on their size, shape, and chemical affinity for the rock, become concentrated in specific zones. One area might become enriched with certain amino acids, while further along the flow path, nucleotides might accumulate. This isn't just a mild enrichment. It can lead to local pockets where the concentration of a particular molecular building block is thousands of times higher than it was in the initial solution. This separation and concentration is a game changer for prebiotic chemistry. For molecules to react and form more complex chains, they need to meet, and they need to do so frequently. In a vast, dilute ocean, this is a slow, chancy process. But in a geothermal field, the chemistry is pre-organized. The right reactants are naturally brought together in high concentrations, dramatically increasing the probability that they will interact and undergo the reactions necessary to form peptides, lipid membranes, or the first strands of RNA. Furthermore, these land-based hot springs experience constant wet-dry cycles as water levels fluctuate and pools evaporate at the surface. As we've seen, these cycles are powerful drivers of polymerization, helping to link small molecules into long chains by removing water molecules. The combination of this cyclical concentration with the internal chromatographic sorting creates an incredibly efficient and organized system for building complexity. The environment itself is also remarkably protective. The mineral-laden water often leads to the rapid formation of hard, siliceous sinters, essentially deposits of opal, that can encase and preserve delicate organic structures, much like fossils. These sinter layers create a sheltered microenvironment, safe from UV radiation and sudden temperature swings, where nascent chemical networks can develop and stabilize over immense spans of time. This presents a holistic and terrestrial pathway, one that doesn't require the immense pressures of the deep sea or the violence of impacts, but leverages the patient, persistent, and organized power of the Earth's own geothermal heartbeat to sort, concentrate, and assemble the molecular pioneers of life. While we've been following the trail of nucleic acids and proteins, there's an entirely different path to life's beginning that focuses not on information, but on structure and separation. This is the lipid world hypothesis, a theory that proposes the very first spark of life wasn't a self-copying molecule, but a simple, self-forming bubble. The central, elegant idea is that the evolution of life began not with genetics, but with geometry specifically, the innate physical properties of certain fatty molecules called lipids. In all modern cells, lipids are the unsung heroes, forming the protective membranes that create a distinct inside and outside, separating the delicate machinery of life from the chaotic environment. The lipid world theory suggests this fundamental act of compartmentalization was the true starting gun. Imagine a quiet, sun-warmed pool on the early Earth, its surface shimmering with a thin, oily film. This isn't just scum, it's a concentrated collection of fatty acids and other primitive lipids, likely delivered by meteorites or formed through geochemical processes. These molecules have a unique duality. One end is hydrophilic, meaning it's attracted to water, while the other end is hydrophobic, repelled by it. When surrounded by water, these lipids don't just float aimlessly, they spontaneously self-organize. To escape the water, their hydrophobic tails huddle together while their water-loving heads face outward, forming a stable, two-layered sheet. And if this sheet is disturbed, it naturally curls in on itself and seals its edges, forming a tiny, hollow sphere, a vesicle. This isn't a conscious act, it's simple, inevitable physics, as natural as a soap bubble forming when you blow air through a ring. These self-assembled vesicles become the world's first protocells, microscopic compartments that could have encapsulated whatever was floating in the water around them. A random assortment of amino acids, nucleotides, maybe even a short strand of RNA or a simple peptide. Suddenly, you don't have a homogeneous soup, you have billions of tiny, individual test tubes, each with its own unique internal chemistry. This isolation is transformative. Within one vesicle, a combination of molecules might be just right to stumble upon a faintly catalytic reaction, perhaps helping to synthesize another lipid. In another vesicle, a different mix might do nothing at all, and this is where the theory introduces its most powerful insight: competition. These lipid vesicles are not static. They can grow not by magic, but by passively incorporating new lipid molecules from their environment, which fuse with their membrane. As a vesicle grows, its spherical membrane becomes increasingly unstable until a gentle disturbance, like a wave or a current, causes it to pinch and divide into two smaller daughter vesicles. This is a primitive, physical form of reproduction with no genetic instructions required. Now, imagine a vesicle that, by pure chance, contains a molecule that slightly accelerates the production or incorporation of lipids. This lucky vesicle would grow and divide a little faster than its neighbors. Its daughters, which would inherit a similar internal environment, would also grow and divide more efficiently. Over time, these more fit vesicles would begin to outnumber the others. This is Darwinian evolution in its most rudimentary form, playing out not with genes but with growth rates and chemical stability. The membrane itself could also have been an active participant, not just a passive bag. Different lipid compositions can have different properties. Some membranes might be more stable in acidic conditions, others might be better at allowing nutrients to pass through. A vesicle with a slightly more permeable membrane might have better access to external building blocks, giving it a growth advantage. A vesicle with a sturdier membrane might survive longer in a turbulent environment. The lipids themselves, through their physical and chemical diversity, could have stored a kind of rudimentary information, a compositional genome that was subject to selection. The lipid world doesn't demand that we choose between metabolism and genetics. Instead, it provides a plausible bridge between the two. These stable, competing compartments could have offered the safe harbor necessary for more fragile molecules like RNA to evolve without being immediately diluted. A primitive ribozyme trapped inside a lipid vesicle would have a captive audience of substrates to act upon, making its catalytic efforts far more effective. The vesicle provided the essential physical framework, the home, within which the more sophisticated chemical tenets of life could eventually move in and thrive. It suggests that the first boundary between life and non-life may not have been a complex chemical reaction, but the simple, beautiful act of a bubble closing in on itself, creating an inside and an outside, and in doing so, creating the possibility of a self. Now, let's zoom in on one of the universe's most versatile and abundant molecular workers, formaldehyde. This simple compound, just one carbon atom linked to two hydrogens and an oxygen, might seem like an unlikely hero in the story of life's origins. It's a common industrial chemical here on Earth, but its true significance lies far beyond our planet, in the cold, dark clouds between the stars. Radio astronomers have detected the unmistakable spectral signature of formaldehyde throughout our galaxy, from the swirling arms of distant nebulae to the vast molecular clouds that serve as stellar nurseries. Its presence is so widespread that it's considered one of the fundamental building blocks of interstellar chemistry. But how does this simple molecule connect to the complex sugars that form the backbone of our genetic material? The answer lies in a remarkably elegant and powerful chemical cascade known as the Formose reaction. Imagine a scenario in the early solar system, perhaps within a warming protoplanetary disk or on the surface of a water-rich asteroid. A concentrated pool of formaldehyde molecules, delivered by comets or formed in situ, is dissolved in water. Under the right conditions, often with a little mineral help from something as simple as calcium hydroxide, or even just a slightly alkaline environment, these identical molecules begin to spontaneously self-organize. The reaction starts with two formaldehyde molecules linking together to form a two-carbon sugar called glycolaldehyde. This is the crucial first domino to fall. Once glycolaldehyde is present, it acts as a catalyst, a kind of molecular recruiter. It readily combines with another formaldehyde molecule, then another and another in a rapid branching chain reaction. The carbon chains grow, adding units in a process called polymerization, transforming from simple 2-carbon sugars to 3-carbon compounds, and then to 4, 5, and 6-carbon sugars. This isn't a slow, plodding assembly line. It's a veritable explosion of molecular complexity from a single, simple starting ingredient. The reaction can produce a whole family of sugars, a diverse mixture that includes pentoses, the 5-carbon sugars. And right there, among that chaotic brew, is one of the most critical molecules for life as we know it, ribose. Ribose is the R in RNA, the foundational scaffold that holds the nucleobases in place to form the very spine of the molecule that may have been the first self-replicator. What makes the foremost reaction so compelling is that it provides a direct, plausible, and non-biological pathway from a molecule we know is abundant in space to a molecule that is absolutely essential for biology. It suggests that the basic framework for genetic material could have been synthesized in abundance throughout the cosmos, long before it was ever incorporated into a living system. The sugar backbone of RNA wasn't necessarily a hard-won invention of early Earth chemistry. It could have been a pre-made cosmic commodity, raining down onto our planet as a finished product ready to be used. Of course, the foremost reaction is notoriously messy. It doesn't just produce ribose, it produces a whole zoo of different sugars, many of which are irrelevant to life, and it can be difficult to control. Furthermore, ribose is a relatively fragile molecule susceptible to degradation. This has led some to question its role in the origin of life. However, this very messiness might have been a feature, not a bug. In a vast prebiotic environment, having a diverse mixture of molecules could have provided a rich library of chemical possibilities for early evolution to act upon. And importantly, recent research has shown that certain minerals, like borates, can help stabilize ribose and steer the foremost reaction toward producing more of the biologically relevant sugars, effectively tidying up the cosmic kitchen. The presence of boron minerals in meteorites lends strong support to this idea, suggesting that natural geochemical processes could have provided the necessary conditions to make this interstellar sugar factory both productive and selective. This theory elegantly links the cold chemistry of interstellar clouds to the warm chemistry of a budding planet, drawing a direct line from a humble, universal molecule detected by our telescopes to the very structure that allows for heredity and evolution. It posits that the sweet core of life's first genetic system might have had a distinctly interstellar flavor. But what if the very first stirrings of life's chemistry were powered not by the chaotic fury of lightning or the deep Earth's heat, but by the simple, abundant, and gentle glow of sunlight? This brings us to a theory that merges the principles of geology, chemistry, and even early electronics, the idea of photoredox chemistry with minerals. To grasp this, we need to think of certain common minerals not as inert rocks, but as nature's own primitive solar panels. Minerals like zinc sulfide and titanium dioxide, often found in the Earth's crust, have a special property: they are semiconductors. This means they can absorb light energy and use it to shuffle electrons around, much like the silicon in a modern solar cell. Now, imagine a shallow tide pool on the early Earth, its bottom glittering with tiny crystals of these semiconducting minerals. The sun rises and its light, particularly the higher energy ultraviolet rays that freely penetrated the primordial atmosphere, strikes these crystalline surfaces. When a photon of light hits a zinc sulfide crystal with enough energy, it doesn't just bounce off or turn into heat. It knocks an electron loose from its usual position in the mineral's atomic structure. This creates a pair, a free, energetic electron desperate to find a new home, and a corresponding electron hole, a positively charged vacancy that is equally eager to grab an electron from somewhere else. This separation of charge is a form of stored energy, and it turns the entire mineral surface into a powerful catalyst for what are known as redox reactions. the very same kinds of electron transfer reactions that power photosynthesis in plants and respiration in our own cells. In this sun-drenched, mineral-rich pool, the stage is set for a remarkable transformation. The positively charged hole on the crystal surface is a potent oxidant. It can pull electrons away from nearby molecules, and one of the most readily available molecules in the early environment was water. By stripping electrons from water, the mineral produces oxygen and, crucially, highly reactive hydrogen ions. Meanwhile, the free, energetic electron is a powerful reductant. It is desperate to donate its extra energy and can do so by forcefully adding electrons to other, stable molecules. A prime candidate is carbon dioxide, a simple gas dissolved in the water that was plentiful in the early atmosphere. By bombarding carbon dioxide with these photo-generated electrons, the mineral can drive a process known as carbon fixation, reducing the inert CO2 and forcing it into new carbon-based configurations. The outcome of this light-driven push and pull on the mineral surface is the synthesis of simple organic molecules. Laboratory experiments have stunningly demonstrated this process. When scientists illuminate a suspension of zinc sulfide particles in water containing dissolved carbon dioxide, they can directly observe the formation of formate, acetate, pyruvate, and other small organic acids. These aren't just random carbon compounds, they are the fundamental metabolic intermediates, the very same small molecules that sit at the heart of the central metabolic pathways in every living cell on Earth today. It's as if the mineral, activated by sunlight, is running a crude but functional version of the Krebs cycle, building the foundational scaffolds of biology from air and water. This theory offers several profound advantages. First, it uses the most ubiquitous and constant energy source available, sunlight. Second, the mineral itself is not consumed. It acts as a perpetual, recyclable catalyst, facilitating reactions without being used up. And third, it provides a direct pathway from the simplest, most universal raw materials, carbon dioxide and water, to the organized carbon structures of life, all without requiring a pre-existing soup of complex organics. It suggests that the first steps toward a living metabolism could have begun on the sunlit, crystalline shores of our planet, with common minerals acting as the essential translators, converting the silent energy of light into the vibrant language of organic chemistry. But while we often picture the origin of life bathed in sunlight or brewing in warm tidal pools, some of the most resilient life on Earth today hints at a radically different possibility, one that unfolds in absolute darkness under immense pressure, completely cut off from the world above. This leads us to a theory that connects the ancient past to a stunning modern discovery, the deep biosphere link. For decades, we assumed life was a surface phenomenon, dependent entirely on the sun's energy. But then we began to drill, and what we found revolutionized our understanding of life's tenacity. We discovered a vast, hidden ecosystem thriving deep within the Earth's crust. Miles below the seafloor, in solid rock, in pores and fissures where temperatures can exceed 120 degrees Celsius and pressures are crushing, we found microbes. Not just a few, but a staggering biomass potentially rivaling all the life in our oceans. These organisms don't live on sunlight, they live on rocks and radioactivity. They subsist on chemical energy, a process called chemosynthesis, and one of their most important power sources is a phenomenon known as radiolysis. Here's how it works. Deep underground, certain rocks, like granite, contain trace amounts of radioactive elements such as uranium, thorium, and potassium. As these elements slowly decay over millions of years, they emit radiation alpha particles, beta particles, and gamma rays. When this radiation passes through the tiny pockets of water trapped within the rock, it doesn't just heat it, it fundamentally breaks the water molecules apart. The radiation shatters H2O into highly reactive fragments, hydrogen gas, hydrogen peroxide, and a variety of potent radicals. This process, radiolysis, transforms stable, inert water into a potent chemical fuel. The hydrogen gas becomes a rich source of electrons, a delicious meal for certain microbes. They can breathe this hydrogen, using it to reduce other compounds like sulfate or carbon dioxide, extracting the energy they need to build their cells and stay alive in the crushing darkness. The existence of this deep, radiation-powered biosphere is a breathtaking fact in itself, but it immediately suggests a profound and thrilling idea for the origin of life. If radiolysis can sustain entire microbial ecosystems today, could it have provided the steady, protected energy and chemical building blocks for the very first prebiotic reactions 4 billion years ago? The early Earth was far more radioactive than it is today, with a hotter interior and a greater abundance of unstable isotopes. This means radiolysis would have been a much more widespread and powerful process. Deep underground, in vast, porous aquifers within the crust, water would have been constantly irradiated, generating a continuous, slow drip supply of hydrogen and reactive oxidants. This environment offers solutions to several major puzzles. First is the problem of concentration and protection. The surface of the early Earth was a violent place, bombarded by ultraviolet light and asteroids. But deep in the crust, nestled within the microscopic pores of rocks, the first delicate organic molecules would have been perfectly shielded. They could have accumulated over millennia, safe from the destruction that ravaged the surface. Second is the problem of a sustained energy gradient. Life and the chemistry that leads to it requires a flow of energy, not just a one-time burst. A hydrothermal vent provides a fantastic but often localized and turbulent energy source. Radiolysis, by contrast, offers something remarkably stable and widespread. The decay of radioactive elements is relentless and predictable, providing a low-level, continuous hum of energy that could have powered chemical reactions across vast volumes of the subsurface for hundreds of millions of years. It's a universal, geological battery, always on. And third, this process directly produces the very ingredients needed for prebiotic chemistry. The hydrogen gas from radiolysis is a powerful reducing agent, perfect for converting carbon dioxide or carbon monoxide into more complex organic molecules. The hydrogen peroxide and other oxidants created could have driven other essential reactions, creating a natural redox chemistry set. In this secluded, rocky labyrinth, simple carbon compounds could have been gradually built up into the acids of life, all powered by the quiet, persistent energy of atomic decay. This theory doesn't necessarily replace other ideas, but rather complements them, suggesting a possible division of labor. Perhaps the building blocks like amino acids and nucleobases were formed in space or in atmospheric reactions and then washed down into the subsurface. Once there, they became concentrated and protected in this deep, radioactive matrix, where the constant energy from radiolysis provided the power to assemble them into more complex polymers and the first self-sustaining metabolic cycles. The deep biosphere link paints a picture of life's origins not as a dramatic event in a warm little pond, but as a slow, patient awakening in the cool, dark, and silent depths of the Earth itself, a genesis powered by the faint nuclear heartbeat of the planet. Returning to the thick, swirling skies of the Hadean Earth, we move beyond the simple gases themselves to consider the very fabric of that ancient air, the countless microscopic droplets and particles suspended within it. This is the world of aerosols, and it offers a uniquely dynamic stage for prebiotic chemistry, one that transforms the entire atmosphere into a vast, three-dimensional laboratory. Imagine not just a blanket of gas, but a misty haze, a permanent, global suspension of incredibly fine particles. These aerosols would have come from a multitude of sources: the fine ash and silicate dust from relentless volcanic eruptions, the salt crystals whipped up from the churning, wave-tossed oceans, and even tiny droplets of sulfuric acid and organic condensates formed naturally from atmospheric gases. Each of these specks, though minuscule on its own, collectively presents an astronomical total surface area. If you could take all the aerosol particles in a cubic meter of that ancient air and lay their surfaces flat, the area would be immense. This is the core of the theory that these suspended particles were not passive dust but active microreactors. Their surfaces provided a solid foundation, a meeting place where molecules from the atmosphere could absorb or stick and be brought into close contact far more efficiently than if they were simply floating freely in the gaseous void. Think of it as the difference between trying to have a conversation in a massive, sparsely populated hall versus around a small, crowded table. Around that table, interactions are inevitable. On the surface of an aerosol droplet, a molecule of formaldehyde might find itself right next to a molecule of hydrogen cyanide. With the added energy from a passing ultraviolet photon from the sun, or perhaps from the heat of a chemical reaction already occurring on the surface, these two molecules could react, forming a more complex compound like glycolonitrile, a direct stepping stone to amino acids. This process of surface-mediated chemistry is dramatically more efficient than gas phase reactions alone. The aerosol surface acts as a catalyst, lowering the energy required for the reaction to proceed, and it also protects the newly formed fragile product. Instead of being isolated and vulnerable, the nascent organic molecule is now stuck to the particle, part of a growing molecular film. This film can become a rich organic coating, a kind of prebiotic varnish enveloping each tiny droplet. As these coated aerosols drift and collide in the atmosphere, they can merge, allowing the molecules from one particle to mix and react with those from another, building even greater complexity in a continuous cycle of combination and growth. But the story doesn't end in the sky. The true power of this aerosol factory lies in its delivery mechanism. These particles don't float forever. They act as condensation nuclei, the seeds around which water vapor condenses to form raindrops. As a droplet grows heavy enough, it falls, washing the precious organic cargo out of the atmosphere and delivering it directly to the Earth's surface and oceans below. This isn't a rare or catastrophic event. It's a constant, gentle drizzle of prebiotic material, a global rain that steadily enriches the primordial soup with a diverse and complex array of compounds synthesized in the skies. This process elegantly solves the dilution problem that plagues many ocean-only scenarios. The atmosphere acts as a massive, planet-wide concentrator and reactor, and the rain acts as a targeted delivery system, bringing concentrated batches of organics to specific locations. A single weather system could deposit a significant pulse of new molecules into a coastal lagoon or a volcanic pond, creating local hotspots of chemical complexity that could then undergo further evolution. Laboratory experiments have beautifully validated this concept. Scientists create chambers that simulate the Hadean atmosphere, complete with water vapor, simple gases, and generated aerosols. When they expose this system to energy sources like UV light or electrical discharges, they find that the aerosol particles rapidly become coated with a complex organic film, a tar-like substance teeming with amino acids, sugars, and the building blocks of lipids. The yield and diversity of molecules are often far greater than in experiments that try to form them in a pure gas or a liquid solution alone. The aerosol environment, with its immense surface area and unique physical chemistry, provides a Goldilocks zone for synthesis, not too dilute, not too chaotic, but just right for building the intricate molecular architecture that would one day assemble itself into the first living cell. Now, as we assemble these molecular building blocks into more complex structures, we encounter one of the most subtle and profound puzzles in the entire origin of life mystery, the problem of handedness or chirality. Look at your own two hands. They are mirror images of each other, similar in structure, but you cannot superimpose one perfectly onto the other. In the same way, many organic molecules, including the amino acids that make up proteins and the sugars that form the backbone of DNA and RNA, also exist in two mirror image forms. Chemists call these left-handed and right-handed versions, or enantiomers. In a standard laboratory synthesis, when you create these molecules from scratch, you always get a perfect 50-50 mixture, a racemic mixture with equal amounts of both left and right-handed forms. Yet, when we look at the chemistry of life, we see a stunning and absolute preference. All living organisms on Earth use exclusively left-handed amino acids to build their proteins, and exclusively right-handed sugars to build their DNA and RNA. This universal trait, known as homochirality, is so fundamental that a protein built with even a single right-handed amino acid would misfold and become dysfunctional. So how did a lifeless, presumably racemic planet commit to this single, uniform-handedness? How did this molecular bias, this broken symmetry, arise? One of the most elegant and cosmic solutions to this riddle points a finger directly at the stars, suggesting that the initial nudge came from a rare and beautiful form of light. This is the theory of chiral selection by circularly polarized light. To understand this, you first have to grasp what circularly polarized light is. Ordinary sunlight is a jumble of electromagnetic waves vibrating in all possible planes perpendicular to its direction of travel. But under certain conditions, this light can become polarized, meaning the waves are organized to vibrate in a single plane. Circularly polarized light takes this a step further. Imagine the tip of the light wave's electric field not just oscillating back and forth, but actually tracing a corkscrew path through space as it travels toward you. It can spiral in a right-handed direction or a left-handed direction. Now, here's the crucial part. A left-handed molecule and a right-handed molecule interact with this spiraling light differently. Just as a left-handed thread will only screw into a left-handed nut, left circularly polarized light will be absorbed more strongly by one enantiomer of a molecule than the other. This differential absorption has a dramatic consequence. It can lead to the selective destruction of one hand over the other. If a racemic mixture of amino acids is bathed in, say, right circularly polarized light, the left-handed amino acids might absorb that light more efficiently. When a molecule absorbs light, that energy has to go somewhere. It often breaks chemical bonds. So, in this scenario, the left-handed amino acids would be preferentially broken down and destroyed, leaving behind an ever so slight excess of the right-handed form. But wait, life uses left-handed amino acids, so for our biology, we would need a source of left circularly polarized light to destroy the right-handed ones and leave the left-handed ones intact. The million-dollar question then becomes, where in the universe could such a specific, biased form of light be found? The answer lies in the dramatic and violent nurseries where stars are born. In regions of star formation, vast clouds of gas and dust are collapsing under their own gravity. As these dust grains, made of silicates and other materials, align in the powerful magnetic fields that permeate these clouds, they can act like a filter. When ordinary starlight from a newborn star passes through this magnetically aligned dust, it can become circularly polarized. Astronomical observations have confirmed this. Telescopes have detected significant levels of circularly polarized light in several star-forming regions, like the Orion Nebula. The handedness of the polarization would depend on the local geometry of the magnetic fields and the orientation of the dust grains. The theory posits that within our own solar system's primordial, planet-forming nebula, certain pockets of dust and gas were illuminated by this polarized light. Any simple organic molecules forming on the surfaces of dust grains in these regions, or drifting through this irradiated space, would have been subjected to this subtle but relentless filtering process. Over thousands or millions of years, this could have imprinted a small but significant chiral bias on the prebiotic material throughout the solar system. The excess might have been tiny, perhaps just a 1% enrichment of left-handed amino acids over right-handed ones, but in the chemistry of life, a small imbalance is all you need to get started. This initial bias could then have been massively amplified through a variety of mechanisms once the molecules were concentrated on the early Earth. For instance, in a process called autocatalysis, a crystal of a left-handed amino acid might act as a template, preferentially encouraging the formation of more left-handed molecules from a nearly racemic soup, snowballing a 1% advantage into a 100% dominance. So, this theory offers a breathtakingly elegant bridge between astrophysics and biology. It suggests that the very same cosmic processes that gave birth to our sun and planets also imprinted upon the raw materials of life a fundamental asymmetry, a slight twist in the molecular fabric that was then seized upon and magnified by the relentless engine of chemical evolution, ultimately defining the left-handed character of every protein in your body, a subtle legacy written in starlight. Now we come to a theory that reimagines the very engine of life's first chemistry, suggesting that before there was a complex metabolism as we know it, there was something far more primal and geochemical. This is the idea of sulfur-driven autotrophic pathways, a concept that places the humble, pungent element sulfur right at the center of the story. Modern life is fundamentally autotrophic at its base, meaning organisms like plants and certain bacteria can build their own complex molecules from simple, single-carbon sources like carbon dioxide. They are the primary producers. This theory proposes that the very first metabolic pathways, the ancestral routines that would eventually evolve into the sophisticated cycles inside our cells today, were also autotrophic, but they were powered not by sunlight but by sulfur. Imagine a world where the foundational chemical networks of life were born not from the assembly of pre-made organic building blocks, but from the direct conversion of planetary gases into biological structure, driven by the reactive power of sulfur. The key players in this ancient drama are gases that would have been abundant in volcanic emissions and around hydrothermal vents, hydrogen sulfide, that classic rotten egg gas, and simple carbon compounds like carbon dioxide or carbon monoxide. On their own, these molecules are relatively stable and inert. Getting them to react and form something new requires a significant push. This is where the environment provides the perfect catalyst. The ocean crust and vent structures are rich in metal sulfides, minerals like iron sulfide and nickel sulfide, which form the very chimneys of black smokers. These aren't just passive rocks, their crystalline surfaces are teeming with reactive sites. A metal sulfide surface can act as a phenomenal geochemical enzyme. It can grab hold of a hydrogen sulfide molecule and a carbon dioxide molecule, holding them in just the right orientation and facilitating a chemical handoff. In this scenario, the hydrogen sulfide isn't a food source in the traditional sense. It's an electron donor, a source of chemical energy. It wants to get rid of electrons. The carbon dioxide, on the other hand, is an electron acceptor. It's hungry for them. The metal sulfide mineral brings them together and mediates the transaction. The hydrogen sulfide is oxidized, and its electrons are used to reduce the carbon dioxide. This reduction is the critical step. It transforms the fully oxidized, inert carbon in CO2 into a more reactive, partially reduced form. Through a series of such surface-catalyzed steps, carbon dioxide can be converted into simple organic acids. The most famous and compelling example of this is the synthesis of acetate, a 2-carbon molecule that is a central hub in modern metabolism. In laboratory experiments that simulate alkaline hydrothermal vent conditions, researchers have observed the formation of acetate from nothing more than hydrogen and carbon dioxide on the surface of metal sulfides like graphite, a magnetic iron sulfide mineral. But the significance goes far beyond making a single molecule. This process represents a primitive but functional metabolic pathway. It's a way of drawing carbon from the environment and using the energy released from sulfur chemistry, building it into a useful carbon skeleton. This is a form of carbon fixation, but it's far more ancient and simple than the Calvin cycle used by plants. It's a geochemical analog to a biological process. The theory suggests that these metal sulfide catalyzed reactions established the first autocatalytic cycles, self-sustaining loops where the products of one reaction facilitate the next, creating a feedback loop that amplifies its own production. The acetate and other simple acids produced wouldn't just float away. They could stick to the very mineral surfaces that created them, becoming available for the next round of reactions. Perhaps two acetates could link together, or an acetate could react with another carbon dioxide molecule, gradually building up the chain length and complexity of the organic molecules right there on the catalytic scaffold. This provides a breathtakingly elegant bridge from pure geology to proto-metabolism. The energy source is the chemical disequilibrium between volcanic gases and the ocean. The factory is the inorganic mineral, and the output is the first generation of organic carbon structures, synthesized directly from a planet's exhalations. It paints a picture of life's chemistry emerging not as a user of a pre-existing organic soup, but as an integrated, dynamic part of the planet's own geochemical cycles, with sulfur serving as the essential, energetic bridge between the mineral world and the biological one. Now, step back for a moment and consider all these disparate theories not as competing ideas, but as individual threads in a single, magnificent tapestry. What if the emergence of organic molecules isn't a rare, fluke event confined to a specific type of hydrothermal vent or a particular planetary surface, but is instead an inevitable, pervasive process woven into the very fabric of the universe? This is the grand, unifying perspective of our 25th theory, which posits that given the fundamental laws of physics and chemistry and the universal abundance of key elements, complex organic chemistry is a natural and widespread cosmic outcome. It's a shift in thinking from a series of lucky accidents to a universal imperative. At the heart of this idea is carbon, the fourth most abundant element in the entire cosmos, forged in the nuclear furnaces of stars and scattered across the galaxy in stellar winds and supernova explosions. Carbon isn't just common, it's uniquely versatile. Its atomic structure allows it to form four strong, stable bonds with other atoms, including itself, creating an almost infinite variety of chains, rings, and branching structures. This tetravalent nature makes carbon the backbone element, the universal Lego brick capable of constructing the intricate molecular architectures of life. But carbon doesn't work alone. It's part of a cosmic consortium of elements essential for life as we know it. Hydrogen, the most abundant element in the universe, is its primary partner. Oxygen and nitrogen, also forged in stars, are ubiquitous. Phosphorus, a key component of DNA and energy-carrying molecules, is found in meteorites and nebulae. Sulfur, crucial for catalysis and protein structure, is common in volcanic emissions and interstellar clouds. The universe, it seems, is not stingy with the ingredients, it's practically throwing them at us. The final ingredient is energy, and the cosmos is overflowing with it. From the gentle, persistent warmth of a young star to the violent shockwaves of a supernova, from the relentless drizzle of cosmic rays in dark clouds to the intense electrical fury of a volcanic plume, energy is the universal currency that drives atoms to break their old bonds and form new, more complex arrangements. What this theory suggests is that wherever you find this specific combination, a sufficient abundance of carbon and its essential partners, along with a source of energy and a stable gradient of temperature and pressure, the slide toward chemical complexity isn't just possible, it's statistically inevitable. It's a natural consequence of thermodynamics and kinetics playing out over cosmic timescales. Think of it like water freezing into ice. When the temperature drops below 0 degrees Celsius, you don't need a special instruction manual or a lucky accident for ice to form. It happens because the physical laws governing water molecules demand it under those conditions. In the same way, when you have a cloud of gas rich in carbon monoxide, ammonia, and water, and you inject energy into it, whether through UV light, shockwaves, or particle radiation, the system will naturally and predictably evolve toward greater complexity. The molecules will react, forming formaldehyde and hydrogen cyanide. These, in turn, will react to form amino acids and nucleobases. Given enough time and the right environmental containers, like the surface of a dust grain or the pore of a rock, these will polymerize into chains. This isn't a goal-oriented process. It's a simple, inexorable drift down a free energy gradient, a natural exploration of chemical possibility space. The evidence for this cosmic imperative is all around us. We detect complex organic molecules in the atmospheres of gas giants in our own solar system. We find them in the swirling masses of protoplanetary disks around young stars. Their spectral signatures are unmistakable in the vast interstellar clouds that stretch between the galaxies. From the simplest clouds of gas and dust to the most complex meteorites, the universe appears to be engaged in a continuous, automated process of organic synthesis. This perspective transforms our place in the cosmos. It means that the chemistry that led to life on Earth is not a solitary, lonely phenomenon. It is a standard part of planetary and even interstellar evolution. The specific pathway that unfolded here, whether it was dominated by hydrothermal vents, radioactive beaches, or cometary delivery, might be unique to our planet's particular history and geology. But the underlying drive, the universal tendency for carbon-based chemistry to complexify under the right conditions, is likely a common feature of our universe. We are not a miraculous exception. We are a local expression of a cosmic law. The emergence of the first organic molecules, therefore, begins to look less like a singular genesis event and more like a phase transition, a point at which a system, driven by universal physical principles, naturally reorganizes itself into a state of higher complexity and order, setting the stage for the even greater marvels to come. While the idea of cosmic factories churning out life's building blocks is compelling, it introduces a new and equally profound puzzle. How do you gather these sparse, scattered molecules from the vast, empty expanse of the solar system and deliver them in meaningful quantities to a small, rocky world like Earth? This brings us to a theory that shifts focus from creation to collection, a grand celestial mechanism known as planetary shepherding and concentration. Imagine the early solar system not as a neat set of orbiting planets, but as a churning, chaotic disk of gas and dust surrounding our infant sun. In the cold, dark reaches beyond the orbit of Jupiter, countless icy planetesimals and cometary bodies are forming, each one a frozen repository of the complex organic molecules synthesized in interstellar space. The problem is, these precious molecular treasures are locked away in the deep freeze, far from the warm, inner region where the rocky planets Mercury, Venus, Earth, and Mars are beginning to take shape. Left to their own devices, these organics would have remained in the outer solar system, forever separated from the worlds most amenable to life. But the solar system had a dynamic and powerful solution: the gravitational influence of the giant planets, particularly Jupiter. As the most massive planet by far, Jupiter's gravity acts as a dominant force, a shepherd of the solar system. During its early migration, as it shifted its orbit closer to the Sun, Jupiter's immense gravitational field would have plowed through the population of outer solar system objects, violently stirring them up. This gravitational perturbation acts like a cosmic slingshot, flinging a vast number of these icy bodies onto new, elliptical orbits that send them diving into the inner solar system. This isn't a gentle delivery, it's a gravitational bombardment, a sustained rain of comets and icy planetesimals that would have pummeled the inner planets during the late heavy bombardment. But from the perspective of prebiotic chemistry, this apocalyptic period was also a period of immense enrichment. Each of these incoming icy bodies was a targeted cargo ship, carrying a concentrated payload of pre-formed organic material directly to the doorsteps of the terrestrial worlds. This process solves the critical problem of dilution in a truly spectacular fashion. Instead of relying on a slow, sparse trickle of interstellar dust, the young Earth was gifted with a veritable avalanche of organics, delivered in bulk by these gravitationally shepherded messengers. The dynamics of this shepherding are even more nuanced and efficient than they might first appear. Orbital resonances play a crucial role. When the orbital period of a small body in the outer solar system forms a simple integer ratio with Jupiter's orbital period, for instance, 2 orbits for every one of Jupiter's, it creates a gravitational resonance. Think of pushing a child on a swing. If you push at just the right moment in the swing cycle, you add a little energy each time, making the swing go higher and higher. In the same way, a resonance with Jupiter can give a gentle but persistent gravitational nudge to a distant icy object, gradually pumping energy into its orbit over millions of years. This doesn't slingshot the object away immediately. It systematically increases the eccentricity of its orbit, stretching it from a near circle to a long, thin ellipse that reaches from the frozen outer belt all the way into the inner solar system. This mechanism acts as a slow, steady conveyor belt, continuously feeding a supply of organic, rich material inward over vast stretches of time. Furthermore, the structure of the protoplanetary disk itself aids in this concentration. As the disk evolved, pressure gradients and drag forces would have naturally caused smaller dust grains and particles to drift inward toward the Sun. Any complex organics coating these tiny particles would have been carried along for the ride, further enriching the material from which the inner planets were accreting. So the picture that emerges is not one of a lucky, one-time delivery, but of a sophisticated, multi-stage celestial logistics network. The outer solar system acts as a vast freezer warehouse, stocked with organic compounds built in interstellar clouds and on icy grain mantles. The gravitational machinery of the giant planets, through migration and resonant interactions, then acts as the supply chain manager, carefully selecting packages from this warehouse and dispatching them on trajectories that cross the orbits of the inner planets. Finally, the inner solar system itself, with its growing rocky planets, becomes the delivery destination, their gravity ensuring that a significant fraction of these incoming shipments are captured and their precious chemical cargo deposited. This theory elegantly reframes the violent early history of our solar system. The same impacts that carved out our moon and scarred our planet's surface were also the primary mechanism for stocking Earth's pantry with the essential ingredients for life. It suggests that the path to a living world may be paved not just by local chemistry, but by the grand, dynamic architecture of its planetary system, where the gravitational dance of giants directly influences the biochemical potential of the smaller, rocky worlds nestled closer to the warmth of their star. But as we pull back from the grand cosmic perspective and return to the intricate molecular machinery of a cell, we encounter a theory that challenges the very centrality of the RNA world by proposing an alternative, and perhaps even more ancient, energy currency for life. This is the Thioester world hypothesis, championed by the renowned biochemist Christian de Duve. It suggests that before there was RNA to carry information, and even before there was ATP to power reactions, the driving force for the very first metabolic networks might have been a much simpler, sulfur-based molecule, the thioester. To understand its power, we need to look at one of life's most fundamental challenges, energy transfer. In all modern organisms, the universal energy currency is ATP, adenosine triphosphate. It's like a microscopic, fully charged battery. When a cell needs energy to build a protein, pump an ion, or fire a nerve signal, it spends an ATP molecule, which releases energy by losing one of its 3 phosphate groups, becoming ADP. This is an incredibly efficient system, but it's also enormously complex. ATP itself is a large, intricate molecule built from a nucleobase, a sugar, and a chain of 3 phosphates. The very existence of ATP implies a pre-existing, sophisticated metabolic network capable of assembling it and then continuously recharging it. This presents a classic which came first dilemma. How could such a complex energy system have bootstrapped itself into existence? The thioester world offers an elegant and chemically simpler solution. Thioesters are a class of molecules formed when a carboxylic acid, a common organic acid, reacts with a thiol, which is a compound containing a sulfur hydrogen group. They are essentially the sulfur-based cousins of the more familiar oxygen-based esters. What makes thioesters so special is their high chemical potential energy. The carbon-sulfur bond in a thioester is what chemists call a high-energy bond, similar in its energetic properties to the phosphate bonds in ATP. This means that breaking this bond releases a significant burst of energy that can be harnessed to drive other, less favorable reactions like linking amino acids together to form peptides or joining nucleotides to create the first strands of RNA. The theory posits that in the sulfur-rich environments of the early Earth, particularly around volcanic hot springs and hydrothermal vents where hydrogen sulfide and reactive metal sulfides were abundant, the formation of thioesters would have been a common and spontaneous geochemical event. Imagine a warm, acidic pool, rich with simple organic acids like acetate and formate, constantly reacting with thiols present in the water or on the surfaces of iron sulfide minerals like pyrite. These reactions would have generated a steady, prebiotic supply of thioesters, creating a natural, planetary-scale reservoir of chemical energy, all without requiring any biological machinery. This provides a plausible energy source for the very first polymerization reactions. A thioester derivative of an amino acid, for instance, is highly activated. In the presence of another amino acid, it doesn't need a complex enzyme to force a reaction. The energy released when the thioester bond breaks can directly provide the push needed to form a new peptide bond, linking the 2 amino acids together. This process could have occurred slowly but surely on mineral surfaces, gradually building up short protein chains or peptides. Similarly, thioester-activated nucleotides could have been the key to forming the first nucleic acid chains, providing the thermodynamic driving force for the otherwise difficult process of dehydration synthesis in water. But the thioester world goes beyond just providing energy for assembly. It also provides a framework for the emergence of the very first self-sustaining metabolic cycles. Duduve proposed that networks of reactions centered around thioesters could have given rise to primitive, autocatalytic cycles, sets of reactions where the products of one step catalyze the next, eventually regenerating the starting material. These cycles would represent a form of metabolism before genetics, a chemical system that can sustain and even amplify itself by drawing energy directly from its geochemical environment. The most compelling evidence for this theory's plausibility lies in its deep connection to core biochemistry that persists in every cell today. The most famous metabolic pathway, the citric acid cycle, also known as the Krebs cycle, is central to how most organisms extract energy from food. In its core, energy-liberating form, this cycle is fundamentally driven by thioester chemistry. A key intermediate, acetyl-CoA, is itself a thioester, and the energy released from its breakdown powers the entire cycle. This is seen as a molecular fossil, a lingering echo from a time when thioesters, not ATP, were the primary energy carriers of the primordial world. So, this theory doesn't necessarily seek to replace the RNA world, but rather to provide it with a necessary foundation. It suggests a stepwise evolution of complexity. First, a thioester world where geochemistry provided the energy for the first metabolic networks and the polymerization of the first crude biopolymers. Then, within this metabolically active, energy-rich chemical system, RNA molecules could have later emerged. Once RNA-based replication and catalysis began, evolution could take over, eventually leading to the refinement of metabolism and the adoption of the more efficient and specialized ATP as the universal energy currency. The Thioester world grounds the origin of life firmly in the chemistry of sulfur and the energy gradients of the early Earth, offering a compelling narrative for how inanimate molecules first learned to capture and spend energy, a fundamental skill that would ultimately pave the way for everything that followed. But our search for the genesis of organic molecules doesn't end with our own planet's past. In fact, one of the most dynamic and promising arenas for this chemistry might be unfolding right now, not on a world bathed in sunlight, but in the lightless, frigid depths of the outer solar system. This is the realm of cryochemistry on icy moons, a theory that suggests the ongoing creation of life's building blocks is a present-day process on worlds like Jupiter's moon Europa and Saturn's moon Enceladus. These are not the barren, frozen wastelands they might first appear to be, thanks to the powerful gravitational tug of war with their giant parent planets. These moons experience intense tidal forces. Imagine taking a ball of clay and repeatedly squeezing and releasing it in your hand. The internal friction generates heat. On a planetary scale, this is tidal heating, and it's enough to melt vast reservoirs of ice deep beneath the surface, creating global, liquid water oceans entirely sealed under a thick, frozen crust. Europa, for instance, is thought to harbor an ocean containing more than twice the water found in all of Earth's oceans combined, despite the moon being only about a quarter of Earth's size. This sets the stage for a truly remarkable environment. At the very bottom of this dark, alien ocean, the water is in direct contact with a rocky, silicate core. This critical interface, where a liquid water ocean meets a geologically active seafloor, is a direct parallel to the hydrothermal vent systems we believe were so important on the early Earth. The tidal heating keeps the core warm, likely driving volcanic activity and creating hydrothermal vents on the ocean floor, where superheated, mineral-rich water spews into the cold, dense brine. This combination of liquid water, a rocky substrate rich in catalysts, and a persistent energy source is the classic recipe for prebiotic chemistry. However, the icy moons add a fascinating, low-temperature twist. The surface of these oceans is a ceiling of solid ice many miles thick. This ice is not a static barrier, it is a dynamic chemical entity in its own right. Bombarded constantly by radiation from Jupiter's and Saturn's powerful magnetic fields, the surface ice is chemically processed. This radiation can break apart the simple water ice molecules, creating reactive oxidants like hydrogen peroxide and molecular oxygen. Over millions of years, geological processes could gradually shuffle this irradiated surface material downward, effectively delivering these potent oxidizing agents into the ocean below. Meanwhile, at the seafloor vents, the reducing environment, rich in hydrogen, methane, and hydrogen sulfide, would be constantly generating its own suite of chemicals. This creates a planet-wide chemical battery, with oxidizing power raining down from above and reducing power bubbling up from below. Where these two contrasting chemical reservoirs meet and mix across the vast volume of the ocean or at specific interfaces, you have all the necessary ingredients for a sustained and diverse organic synthesis. The evidence that this is not just theoretical is breathtaking. The Cassini spacecraft, while orbiting Saturn, flew directly through the massive plumes of water vapor and ice crystals erupting from fissures in the south pole of Enceladus. Analysis of these plume particles revealed that they are not just pure water ice, they are laced with a surprising array of complex organic molecules. We're not just talking about simple precursors. Scientists detected compounds with molecular masses well over 200 atomic mass units, which indicates the presence of large, intricate carbon-based structures. Even more recently, data from the James Webb Space Telescope has suggested the presence of a vast plume erupting from Europa as well, hinting that its hidden ocean is similarly rich in chemical activity. This means that the kind of chemistry we speculate occurred on Earth 4 billion years ago is likely happening at this very moment in the subsurface oceans of these distant icy moons. They are natural, ongoing laboratories for cryochemistry, where the freezing temperatures, immense pressures, and unique energy sources might be forging organic molecules along pathways we are only beginning to understand. The discovery that such complex organics can form and persist in these environments dramatically expands the possible habitats for life's initial steps, suggesting that the universe's capacity for organic synthesis is not a relic of the past, but a vibrant and ongoing cosmic process. And this brings us to a fundamental and often overlooked element in the grand assembly of life, a nutrient so crucial that its scarcity might have been one of the final, formidable barriers life had to overcome. This is Theory 29, and it centers on the surprising role of phosphorus, and a very special mineral from space that may have unlocked it for the very first time. Phosphorus is absolutely indispensable for every known form of life. It forms the very backbone of the DNA and RNA molecules that carry our genetic code. It's the key energy-carrying unit in ATP, the molecule that powers every cellular process, and it's the fundamental building block of phospholipids, the molecules that create the protective membranes of every single cell that has ever existed. Without phosphorus, there is no genetics, no energy currency, and no cellular life. Yet, for all its importance, phosphorus presents a profound paradox known as the phosphorus problem on the early Earth. While phosphorus itself is relatively common in the planet's crust, it's almost always locked away in highly insoluble minerals, primarily apatite. Think of it as a treasure that's been sealed inside a nearly indestructible vault. In its natural, rocky form, phosphorus is chemically inert and virtually unavailable for life's chemistry. Water cannot dissolve it effectively, meaning that in the primordial oceans, this vital element would have been present only in trace amounts, completely inadequate for synthesizing the vast quantities of nucleotides and phospholipids needed to kickstart biology. So, how did life get its hands on this locked-away treasure? The answer may have fallen from the sky in the form of a unique and highly reactive iron-nickel phosphide mineral called schrebersite. This mineral is not a common feature of Earth's native geology. It is, however, a frequent and significant component of iron meteorites. When these meteorites plunged through the early atmosphere and landed in Earth's watery environments, something remarkable happened. Unlike the stubbornly insoluble apatite, schrebersite is highly reactive in water. Upon contact, it undergoes a process called corrosion, slowly dissolving and releasing its phosphorus not as a locked-up phosphate, but in a far more chemically accessible and reactive form known as phosphite. This distinction is everything. Phosphite is a more reduced form of phosphorus, meaning it carries more electrons, making it far more eager to participate in chemical reactions than its oxidized phosphate cousin. In the warm, slightly acidic waters of early lakes, rivers, or even hydrothermal pools, this meteoritic schrebersite would have acted as a slow-release phosphorus pill. Laboratory experiments that simulate these conditions have produced stunning results. When a piece of schrebersite is placed in water mimicking the prebiotic environment, it doesn't just sit there. It corrodes, creating a complex mixture of phosphorus-containing compounds, including phosphite. And in the presence of other simple organic building blocks, this reactive phosphorus readily incorporates itself into life's essential molecules. Researchers have observed the direct formation of phosphorylated molecules, the critical first step in building nucleotides. Even more impressively, under the right conditions, these reactions can yield the fundamental structures of phospholipids, the very molecules that spontaneously assemble into cell-like vesicles. This isn't just a minor chemical curiosity. It's a direct pathway from an inert space rock to the activated precursors of genetics and cellular structure. The implications are profound. It suggests that the late heavy bombardment, that period of intense asteroid and comet impacts, wasn't just a destructive era or a simple delivery service for generic organic compounds. It was a targeted fertilization event, specifically enriching the young Earth with a highly bioavailable form of a key limiting nutrient. Each iron meteorite that crashed into the planet was not just a lump of metal. It was a package of reactive Schreibersite grains scattering into the environment and acting as countless microscopic phosphorus factories, slowly leaching this essential element into the water in a form that prebiotic chemistry could actually use. This elegantly solves the phosphorus problem by providing a plausible, abundant, and geologically attested source. It connects the violent, extraterrestrial history of our solar system directly to the most intimate structures of biology, proposing that the very framework of our cells and the backbone of our genetic code might owe their existence to the reactive heart of ancient meteorites, a gift from the cosmos that literally helped build the walls and the blueprints of life itself. And so, after exploring this vast cosmos of possibilities, from the cold, dark clouds between the stars to the fiery, churning depths of our own young planet, we arrive at a final, synthesizing insight. The sheer number and diversity of plausible theories is not a sign of scientific failure, but a profound clue in itself. Perhaps the most compelling answer to the mystery of life's first molecules is not a single, triumphant theory, but a grand, collaborative symphony where many different processes played their unique and essential part. This is the hybrid, multi-stage model of life's origin, a framework that suggests the journey from chemistry to biology was not a single, fragile thread, but a resilient, interwoven tapestry of cosmic and planetary events. Imagine the early Earth not as a single laboratory, but as a sprawling, planet-wide research and development campus, with different departments specializing in different stages of the production line. The first stage was universal provisioning, a cosmic supply chain that operated on a galactic scale. In the frigid nurseries of interstellar molecular clouds and on the surfaces of countless comets, the most basic building blocks were being manufactured. Cosmic rays and ultraviolet light forged amino acids and nucleobases in the ice mantles of dust grains, while the chaotic chemistry of the protoplanetary disk churned out sugars and fatty acids. This wasn't a targeted effort, it was a universal background process, ensuring that the raw ingredients for life were a common feature of the cosmos. Then, during the violent infancy of our solar system, the gravitational machinations of the giant planets acted as the logistics managers, shepherding these organic rich comets and asteroids inward during the late heavy bombardment. This period of cosmic violence was paradoxically a delivery service of unparalleled generosity, stockpiling Earth's pantry with a rich and diverse inventory of pre-formed molecular parts. With the raw materials delivered, the next stage could begin, concentrated assembly. This is where the deep-sea environments, particularly the alkaline hydrothermal vents, took center stage. These remarkable structures were far more than just sources of heat and chemicals. They were nature's most sophisticated prebiotic factories. Their porous, rocky mounds provided a safe haven, completely shielded from the destructive ultraviolet radiation at the surface. More importantly, they offered a perfect combination of things the dilute ocean could not: immense surface area for molecules to adhere, a constant flow of chemical energy from the reaction between hydrogen-rich vent fluid and carbon dioxide-rich seawater, and a natural, sustained proton gradient across their mineral walls that acted as a primitive geochemical battery. Within these microscopic pores and channels, the scattered organic molecules delivered from space could become highly concentrated. The mineral surfaces, rich in iron and sulfur, acted as both catalysts and templates, shepherding the chemical reactions that linked amino acids into short peptides and nucleotides into the first strands of RNA. The vent environment provided the sheltered, energy-rich workshop where the initial, clumsy steps toward metabolism and replication could begin. But while the deep sea provided the perfect nursery, the final touches may have required a different kind of environment altogether. This is where the surface world, once considered too hostile, re-enters the story as a crucial finishing school. The products of the vent systems, primitive metabolic cycles, short RNA strands, and lipid molecules would have eventually been circulated into the wider oceans. Washed ashore into sun-drenched tidal pools or geothermal lagoons, these molecular pioneers encountered a new set of powerful forces. The constant cycles of wetting and drying in these pools are incredibly effective at driving polymerization, helping to form longer and more stable chains of RNA and peptides. The photoredox chemistry on mineral surfaces in shallow waters could have provided a new energy source, refining the molecular structures, and the simple physics of lipid self-assembly in these concentrated pools would have made the formation of protocell vesicles, the first cellular compartments, almost inevitable. In this hybrid model, no single environment had to do all the work. The cosmic clouds provided the universal parts kit. The hydrothermal vents provided the safe, powered workshop for initial assembly. And the dynamic surface environments provided the testing ground where these components could be refined, encapsulated, and set in competition with one another, allowing natural selection to begin its work at the molecular level. This multi-stage process is not just a convenient way to combine all the theories. It solves the fundamental weaknesses of each one in isolation. The dilution problem of the primordial soup is solved by cosmic delivery and vent-based concentration. The instability of surface molecules is solved by the deep sea sanctuary. The lack of a driving force for polymerization is solved by the unique energy gradients of vents and the wet-dry cycles of tidal flats. This robust, multi-pronged approach makes the emergence of life seem less like a miraculous fluke and more like an almost inevitable outcome of a planet positioned within a rich cosmic ecosystem and possessing the right geological diversity. It suggests that life is not a fragile spark but a resilient flame, one that can be kindled by many different hands across the universe, following a universal script written in the laws of chemistry and physics. Stepping back from this breathtaking tour through 30 different possibilities, the sheer number of theories isn't a sign of confusion, but rather a testament to the incredible creativity and rigor of the scientific search itself. What emerges is not a single, tidy answer, but a sprawling, dynamic map of potential pathways, each with its own compelling evidence and its own unique challenges. When we analyze them together, we see common threads that weave through many ideas and stark contradictions that highlight the deepest puzzles still facing researchers today. One of the most powerful commonalities is the universal need for concentration and a protected environment. Whether it's the microscopic pores of a hydrothermal vent, the layered structure of a tidal flat, or the surface of an interstellar dust grain, the story is the same. A dilute soup of ingredients is not enough. Life's chemistry demands that molecules be brought into close, intimate contact, shielded from the dispersive forces of a vast ocean or the destructive power of UV radiation. This is a theme that unites the iron-sulfur world's sticky pyrite surfaces with the aerosol theory's microscopic droplets and the lipid world's self-assembling bubbles. They all recognize that the transition from chemistry to biology requires creating a local pocket of order, a sheltered workshop where reactions can proceed without being constantly washed away or torn apart. Another unifying thread is the central role of energy gradients. Life is not a static state. It's a process that requires a constant flow of energy to maintain its complexity. The most plausible theories all tap into powerful, sustained energy sources that were readily available on the young Earth or in space. The alkaline vent theory leverages the chemical battery of a natural pH difference. The radioactive beach harnesses the steady decay of unstable atoms. Photoredox chemistry captures the relentless energy of sunlight, and the deep biosphere theory runs on the slow, geologic hum of radiolysis. What's fascinating is that these are not fleeting bursts of energy like a single lightning strike, but persistent, reliable gradients that could have powered chemical reactions for millennia, providing the stability necessary for complexity to slowly accumulate. Yet, for all these common threads, major contradictions define the vibrant debates at the heart of abiogenesis. One of the most fundamental divides is the question of metabolism first versus genetics first. The iron-sulfur world and alkaline vent theories present a powerful vision where energy harvesting, self-sustaining metabolic cycles emerged first, pinned to mineral surfaces. In this view, the complex molecules of genetics, like RNA, were later inventions that grew within these pre-existing metabolically active systems. It's a bottom-up approach, building complexity from energy flow. The RNA world hypothesis, in stark contrast, argues that replication and information storage had to come first. It posits that without a molecule capable of copying itself and undergoing evolution, no sustained chemical system could truly take off. This is a top-down approach where the informational molecule is the seed from which everything else, including metabolism, eventually grew. These are not easily reconcilable viewpoints. They represent two profoundly different visions of life's most essential starting principle. The debate also rages over the very location of life's cradle, creating a stark geographical contradiction. Was it the deep or the shallow? The deep-sea vent scenarios offer unparalleled protection and a continuous energy source, arguing that the surface was far too violent and destructive for delicate chemistry. Conversely, theories centered on tidal pools, radioactive beaches, and photochemical aerosols argue that the surface world, with its dynamic cycles of wetting and drying and its access to diverse energy sources like sunlight and atmospheric chemistry, was essential for driving key processes like polymerization. The deep offers stability, while the shallow offers dynamic change and concentration mechanisms. Both have compelling advantages that are difficult to ignore. Perhaps the grandest contradiction of all lies in the question of extraterrestrial contribution versus purely terrestrial origins. Panspermia and the cometary factory model present a universe that is preloaded with life's building blocks, suggesting that Earth's role was merely to provide a hospitable environment for assembly, not invention. This elegantly solves the problem of synthesizing complex molecules from scratch. On the other hand, theories like the primordial soup, hydrothermal vents, and the iron-sulfur world demonstrate that such synthesis is entirely possible under early Earth conditions. The contradiction here is one of emphasis. Is life a cosmic imperative with its ingredients widespread throughout the galaxy? Or is it the specific, hard-won achievement of a unique planetary chemistry lab? The truth likely incorporates both, but the balance between them remains a central point of discussion. So, which environments and energy sources emerge as the most promising from this cacophony of ideas? While no single theory has yet claimed victory, a powerful synthesis is gaining traction. The hybrid, multi-stage model seems to resolve many of these contradictions by assigning different stages of the process to different environments. In this view, the universe provided the initial toolkit through interstellar and cometary chemistry. These precious ingredients were then delivered to Earth, where the deep-sea alkaline vents acted as a protected, powered incubator, concentrating the molecules and fostering the first metabolic and replicative systems. Finally, these nascent systems were circulated to surface environments like tidal flats, where wet-dry cycles and new energy sources helped refine them, encapsulate them into the first protocells, and set the stage for Darwinian evolution to truly begin. This integrated approach doesn't force us to choose one theory over another, but rather sees them as chapters in a single, epic story. The dynamic and ongoing debate in abiogenesis is not a sign of failure, but a sign of a healthy, thriving field, one that is constantly testing, refining, and synthesizing ideas in our relentless quest to understand our own deepest origins. From the crushing pressures of hydrothermal vents to the frozen, silent laboratories of interstellar dust grains, our journey through these 30 theories reveals a cosmos that is fundamentally, astonishingly creative. We began with a universe of simple, sterile gases and followed the trail of carbon as it weaves itself into ever more complex tapestries, from the humble amino acids of the primordial soup to the intricate, self-assembling membranes of the lipid world. We have seen how energy, whether from the violent shock of an asteroid impact, the gentle decay of a radioactive atom, or the persistent gradient across a mineral wall, acts as the universal currency that drives this grand chemical evolution. The sheer number of plausible pathways is not a sign of scientific uncertainty, but a profound testament to a central, unifying theme. The universe appears to be hardwired for organic chemistry. It seems that wherever the fundamental ingredients of carbon, hydrogen, oxygen, and nitrogen are brought together with a source of energy and a stable environment, the slide toward chemical complexity is not just possible but statistically inevitable. This transforms our perspective from one of lonely exception to one of cosmic participation. We are not a miraculous fluke in an otherwise dead and empty void. The evidence gathered from meteorites, from the telescopes peering into nebulae, and from the robotic explorers sampling the plumes of icy moons, all points toward a single, breathtaking conclusion. The universe is not merely habitable, it is potentially prolific, a vast and fertile ground where the seeds of life can be sown again and again. The building blocks of biology are a universal constant, a common inheritance shared by every nascent star system. This grand synthesis suggests that the origin of life on Earth was likely not a single, fragile event, but a resilient, multi-stage process. It was a collaboration between the cosmos and our planet. The outer solar system and interstellar space provided the raw molecular feedstock. The dynamic architecture of our planetary system, shepherded by the gravity of giants like Jupiter, ensured a generous delivery of these materials. And once here, our own world provided a diverse portfolio of specialized laboratories, the protected pores of alkaline vents for concentrated assembly, the sun-drenched tidal flats for polymerization and encapsulation, and the deep, radioactive crust for stable, long-term experimentation. No single environment had to do all the work. Our planet's geological diversity offered a full suite of tools for the job. The question then shifts from a desolate, "Are we alone?" to a far more thrilling, "Where else has this process taken root?" The ongoing, active organic chemistry we now see on moons like Enceladus and Europa tells us that the story is not confined to the distant past. It is happening now in our own cosmic backyard. This quest, therefore, is far from over. It is an invitation to keep looking, to keep questioning, and to keep sending our robotic emissaries to the furthest reaches of our solar system and beyond. Each new discovery, each refined theory, brings us closer to understanding our own place in this grand chemical narrative. We are stardust that has awakened, and our search for our own origins is ultimately a search for our cosmic kin. The universe is not silent, it is humming with molecular potential, and we are only just beginning to learn how to listen, so we turn the question over to you. After this journey from the depths of the ocean to the heart of the galaxy, which of these pathways resonates most deeply with you? Is it the elegant simplicity of the primordial soup, the structured power of the iron-sulfur world, or the cosmic promise of Panspermia? Let us know your thoughts in the comments below, and if you enjoyed this deep dive into the genesis of life's molecules, be sure to subscribe so you don't miss our next exploration into the profound mysteries of the cosmos.